Okay, so today we are going to introduce Ionic Equilibria as I told you. So first things first, let's see what the syllabus wants us to learn as far as this topic is concerned. But before we even go any further, I want you to look at the name of the topic generally. So I told you it's a topic of Senior 5 Term 3. Senior 5 Term 3. And the very general topic is Equilibria 1. And I told you it may or may not be an element of construct. So I told you that under this, we cover chemical equilibrium. That is the very sub chapter that we began with. 7.1, that one was covered. Then this is just concerning application. It's not a big deal. It is just under this. Yeah. Because they talk of equilibrium and the chemical industry. And that application is just under chemical. As simple as that. So, the third subtopic is here. That is ionic equilibrium, hydrolysis of salts, then buffer solutions. So the general topic, this is where we find acids, bases, and salts. But for salts, we strictly look at what? Hydrolysis, or their hydrolysis. So that means ionic equilibria is the one that takes on the acids and the bases. Then when we begin salts, we just look at their what? Their hydrolysis. Then we end with buffer solutions, and it will be done. So when buffer solutions are done, then this one can be to the solubility equilibria. Something like that. Then from there, we go to Equilibria 2. And you all know that in Equilibria 2, this one was covered. That is phase Equilibria. And we only have one to go under Equilibria 2. That is senior 6-term work. And that is colligative properties. And we shall also handle them. So with chemistry, I just believe we are not so badly off. We are not. Those who will be listening to this in the future, you never know. Colligative properties will be present. Even ionic equilibrium will have been done. And this is your first lesson, and you have more 4 lessons to go. Okay. Now, hope you've gotten that. That this is the topic that replaces acids, bases, and salts of all level. Salts, we only look at their hydrolysis, which is here. Then the ionic equilibrium part is what takes on acids and bases. Why I'm wasting my time here, students have been asking me, and they have always asked me for years, that what is the difference between ionic and chemical equilibrium? Are they the same or they are different? For phase, someone understands after they have covered, but people have a tendency of confusing those equilibria. But I've tried my best. The chemical is where you find the Kc, the Kp, and so on. And it's where you end with the Chatelia's principle. Then for ionic equilibrium is where you talk about acids, bases, and salt, then buffer solutions. And for this side, we find the Ka, the Kb, the Kh, and pH, POH, pKb, Kb, those things. They're the ones we find this side. So hope you get that simple introduction. Okay, now I can tell you the fact. So the fact is that as far as this ionic equilibria is concerned, I'm going to strictly talk about acids, I'm going to talk about bases. You all know that the other part of salt is just their hydrolysis, and it's an independent topic. So these two have lesson targets in common. Yeah, we cover the same things here. Yeah, the same things are what? Are covered. So, what do I mean? We are supposed to first and foremost define. We should try to define. Or I can first say their meaning. So you need to get us the meaning of each. Then I think after that, we can talk about the theories of ionization of each. And that's where the most chemistry is. Yeah. Then we should find time and talk about the properties then we should talk about the types of each. And examples in each case. Then I want us to end with the equations of ionization in each case. Equations of ionization in each case. Then you all know, I never leave the lesson without research and assignment. Then since this is just lesson 1, that means lesson 2 must exist. So I'll tell you our next stop. Yes. And that will be the end. And trust me, that will be enough. That will be enough for today. If God helps us and we complete all that as I've listed it and you get it, that means we shall be soon reaching PH. And that's how we shall go to KH. And as you can see, I'm only interested in only this part, this one. According to the syllabus book, that this is the only part we are going to cover. But you can see part C is salts. That means acids and bases are just here, which is not fair. But we are going to try our level best. So the next time we shall be handling the acid and base dissociation constants. And then in the other lesson, we shall be handling the pH concept. We do calculations, then we go to salts like that. It's a very long topic, even when you look at this and you think they're actually very little, but it's very huge. The pH concept alone is very huge. The constants are not easy. You need an open mind, so listen carefully. Let's achieve these targets together and leave this place early enough. So, to begin with, is the meaning of each. Yes, what's the meaning of the acid? What is the meaning of the base? After that, what are those theories that came up when they were looking at defining these things and so on and describing their nature? Okay, now to begin with, I'll begin with the acid. I'll begin with the acids. So I'm going to give anyone a chance. You know our lessons 1, they are always interactive. So I want someone to just tell me one thing they know about acids. Just one thing. Because we haven't started defining, but I just need one thing you know about acids. Anything from all level. Yes, breather.
An acid is a proton
Proton. Thank you so much. Yes, Richard. Yes, Richard.
It was the same, a proton donor.
Yes, Nicholas. Thanks, Richard. Yes, Nicholas. I think Nicholas doesn't have anything to say. Yes, Cecil, there is something that I want.
They are characterized by a sour taste.
Okay, that is also good. Okay, thank you for your submissions, people. Now, the other thing that is most obvious, someone has talked about their test. Their test will come in as we talk about the properties. But one thing that I'm sure of, is that you know that these acids, they ionize. They ionize. I remember teaching you this when I was teaching you chemical equations. That when they say ionize, that one means producing ions. And I told you that producing ions happens when something is dissolved in water. Happens Yeah, you just learned that. But when I mention the word ionize, what am I simply meaning? I'm simply meaning that when you dissolve that thing in water, it will produce ions. So they ionize in water. Produce hydrogen ions. As simple as that. In O level, we used to add on as the only positively charged ions in solution. But that's not a point here. In A level, no one will ask you to define an acid. You just need to know its meaning. So one thing I just want to add on that the hydrogen ions, you need to understand that they are positively what? They are positively charged. Yeah, very important to note. So for you to write the structure of the hydrogen ion without putting a plus is very risky. Get the point? Now, if you want to write how they are denoted, this is what you do. Are denoted as hydrogen H, but with a plus like that. Very important. Now, after you looking at that structure, we have been having that structure so much in organic chemistry. And I want to ask people for a recall and guidance. I want you people to tell me. We were doing these things in organic chemistry, and guess what? We used to have it, maybe we used to have such a step. We have via O, we have via plus, we have via H, and we also have via H. Then, after that, I want to see the good organic chemists here. So we used to come, put the arrow, then we get only this, or we remain with only the OH like that. Then we used to bring the arrow here like that, and then we do this. That one was explained, I'm not re-explaining. I just want someone to remind me, what is the name of this? What did we say? What's the name of that? What is the name of that? What is the name of that? How did we use to call that? Maybe I can say this was any group. If I don't put anything, who can tell me? How did we use to call that? You write it in the chat. That was our group R. Our group R. How is this one called? Yes, that's the word I want, proton loss. Yeah, you people are saying proton loss. Very good, proton loss. Now, you people, why we call it proton loss? Why we call it proton loss is this. This is why we call it proton loss. So why we call it a loss is because of this minus. That's why we call it what? A loss. So if I'm to match, that's how I match. Why we call it now proton loss? It's because the H plus is the proton. You get the point? Why loss minus? Like we have lost the H plus. So you realize that the H plus is what they are calling the proton. Yeah. That's why you may find people just calling it hydrogen ion loss. But we just simplify it and call it proton loss. The English people call it deprotonation, which is okay also. You understand? So one thing that I want you to realize is that this one is also called a proton. It's also called a what? A proton. Now, if it's called a proton, I will give you the hence part. And I will tell you that hence, we can come up and say acids produce. And I told you that when they say in water, they mean ionizes. So you people, if acids produce protons, because all we know they produce hydrogen ions, but we are like hydrogen ions are also called what? Protons. So if they produce protons, are they acid donors or are they proton donors or they are proton acceptors? So we shall have another hence. If they ionize to produce hydrogen ions, which are protons, that means they ionize to give us protons. So are they donating or they are accepting? The protons are proton. That means what people are saying. Proton donors. People have a very wrong spelling, which is bad. Okay, you people, they are ionizing and they are giving us protons in solution. So they are donating the protons. So they are called proton donors. That is the right spelling. We don't have A anywhere. So you correct that. So those are the two things I wanted to tell you. Yes, concerning the acids. That can be the meaning. You can have such a meaning. Ionizing in water. So the reverse is true. The reverse is true for bases. And that's what we are going to do. Yeah. So when now I come to bases, just their meaning. We are just getting the reverse, nothing else. So bases, these ones ionize. So this time around, let me put for you the statements so that you appreciate the chemistry. So these ones dissolve in water, and after dissolving water, what happens? They ionize. You get, and after ionizing, what happens? They produce. Acids produce hydrogen ions. The opposite of hydrogen ions in chemistry, they are the hydroxide. So to produce hydroxide ions, this is a level. You don't need to say as the only negatively charged ions in solution. After all, no one is going to ask you to define. So you just need to note and tell them that these ions are negatively what? charged. They are negatively what? Charged. Then also the other thing you should note is that they can also be called. Yes, Rebecca. Yes, Rebecca.
Doctor, I'm inquiring on that if I don't know if that's what you're talking about next, but if hydroxide and hydroxyl are the same.
Yeah, it's what I'm going to talk about briefly. So they are also called hydroxyl. Yeah. So when you find a question having hydroxyl, just understand they are talking about hydroxide. But I'm going to advise you, don't use it. I don't know if people are getting me. Don't use it, and I'm going to tell you why. When you find the question saying hydroxyl ions, understand they are talking of what? Hydroxide ions. But you don't use it. Like, don't forcibly use it when it has not been said in the question. Someone may be saying, why? After us saying they are negatively charged, all of you here know how they look like. Because I told you that in chemical formula, so hydroxide ions, they are denoted as this. Are you seeing how they look like? But I also don't want you to be surprised when you find them like this. OH, but with the negative here. Are you seeing? But I'm going to tell you that I'm going to give this one 3 ticks, and I'm only going to give this one 1 tick, because this one is better when the negative is on top of the O. The moment you put it on top of H, that is wrong. So either put it on top of O or put it after the H. But the one when the negative is on top of O is better. So why don't I want you to use it forcibly? This is what I always tell my students. That if at all you are talking of hydroxide, then hydroxyl, those are the two words. When you say hydroxide, let it be the ion, which is like this. That's the better way. If it's hydroxyl, let it be the group. Do you know the hydroxyl group in organic chemistry, which they write like that? I don't know if people now get it. That's what I usually tell my students. That if you're deciding, if I turn off these notifications, if you decide and say that if you decide and say that for me, I'm going to use the word hydroxide, I expect it to be the ion. When you say that I'm going to use the word hydroxyl, I expect it to be the hydroxyl group, which is in what? In organic chemistry. Hope you understand. Yeah. So I think we can now go to other things. Okay, I think I'm done. Yeah. Okay. Now, that is the brief information about bases, dissolving in water, ionizing, giving you those ions, and so on and so forth. The other thing I want to tell you is that the word ionizing is better. But sometimes, okay. Ionize is to dissociate. So, if at all you find the word dissociate instead of ionize, or when we begin using dissociate instead of ionize, you please appreciate it. Now, after that, we want to see, what do these hydroxide ions really want? What do they really want? I've told you the reverse is true. The reverse is true for bases. So for acids, we saw they donate protons in solution. That means bases, we always do what? Accept. And how will they accept? So have it in mind that if this is our base and it produces the hydroxide ion, have it in mind that the hydroxide ions can attract the H+. That is something very clear. Because we are talking of attraction, and after talking about attraction, you can see this one is a negative and this one is a positive. So of course attraction can happen. And then you know when they interact, they will form what? They will form water. Something like that. And formation of water, because we all know from O level that water has a neutral pH. Water has a what? A neutral pH. So the formation of water, the formation of water which one? When the OH interacts with the H plus to form the water. You all know this is aqueous because we are in a solution. This is aqueous and this is a liquid. You know all those states. So I don't want us to go into too much details for now, but that arrow is reversible. But for now we can just have it like that. But for matters of being serious, I can just include it and say, okay, we are in a solution, so aqueous. We are in a solution, so aqueous, and the water we are forming is a liquid. So that's what they call a neutralization reaction. This one is called a neutralization reaction because we are forming water, which water has a neutral pH. We shall see that with time. So this is what we call a neutralization reaction. Okay, now I want you to listen. Instead of saying the word attract, I can say accept. And instead of the H plus, I can say proton. Get the point? So I can literally say that the hydroxide ion from the base can accept the proton from the acid. And that's what will make these bases proton acceptors. So now I'm going to modify these statements. That these bases only accept protons from an acid because it's acids that provide proton acceptors from the acids. Those are the bases. And then the acids we talked about earlier as the proton donors. Have it in mind that they are proton donors to bases. Yes, because it's bases that are there to accept those protons. Those are the complete statements. They donate protons to bases, and bases accept protons from acids. So we've talked of acids producing hydrogen ions. We've talked of them donating protons. We've talked about the reverse for the bases, them producing hydroxide ions, and also them being proton acceptors. Acids donate protons to bases, bases accept protons from acids. Now, that is the general meaning. We have not looked at any equation. The equations are going to come later on. They are going to come later on. They are going to come later on. Before we go to the equations, let's first take the first learning target. Those who think we are not moving, we are. So the meaning of each is done. Before we go to the properties of each, let me first take you through the theories of ionization. Very fast. The theories of ionization. So, as they were introducing these things of acids, bases, and so on, a lot of theories came up. Different people came with their own perspectives as far as acids and bases are concerned. And those perspectives have been already discussed. I'm going to just attach a perspective to an individual. A perspective to an individual. There were 3 groups of people. And I'm going to do 2 groups. I leave you with one as research. And the one I'm leaving for as research is the one that is not so common. So, very first, the theories, which was the very first. Let's look at the theories of acids and bases, but their theories are strictly about how they ionize or how they behave. So this is what I want you to understand. This is what I want you to understand. Remember, we are having acids, we are having the bases. Here we shall have the theory. Of course, the theory will show us the individual. Okay, now there is that first format of definitions, which was talking about producing hydrogen ions. So there's when we talked about producing what? Hydrogen ions. Then we said the reverse is true for bases, and we talked of producing what? Hydroxide ion. Then there is that one of protons, and we said acids, we prefer them being proton what? Donors. But we say they donate to bases. Then there is that one of proton acceptors for bases, and we say they accept from acids that produce them. So proton what? Acceptors, like that. Then there is the last one. So I'll put dashes. So this one, told you I never leave any lesson without research. That is your research. This one is your research. Okay. Now, one thing I want you to understand about theories is that these theories give us the names of the individuals. Yeah. So these theories are names of the individuals that gave us their perspective. Yeah. Names of the individuals. Okay. Now, concerning the theory that was talking about hydrogen ion and the hydroxide ion, that one was known as the Arrhenius theory. So we shall see the equations later. So provided our equation is in such a format, you just need to learn these things and appreciate them. No one is going to examine Arrhenius. They really examine application of these things, but they are part of the syllabus, so we have no option. So that was Arrhenius. When we say Arrhenius theory, we mean that the person who brought that perspective of hydrogen ions and hydroxide ions was called Arrhenius. Then concerning donating and accepting protons, there were two people. And that was Bronsted and Lowry. Bronsted and Lowry, like that. Yeah. So Bronsted and the girlfriend came up with that theory for donating and accepting protons. So you can see long ago relationships were meaningful to the academic sector. Unlike now, where you and your girlfriend are known for one thing, and that is double dealing. They are aware that that couple can never leave the dining hall unless the chefs of the school have taken away the saucepans. Those days, Bronsted and the girlfriend sat down and did something important. They said acids can donate protons, bases can accept. Then there is you. Okay. So there's the last theory, and that was the Lewis theory. So Bronsted, Lowry, there are two people. Eh? Then we have Lewis theory. So you find out Lewis theory. What did Lewis say about acids? What did Lewis say about bases? As simple as that. So when I go back, I'm going to come and tick this. So we are moving. Eh? We are moving. I told you we shall complete the targets by force. My emphasis is here. Only. No pressure. No pressure. Why I don't have pressure? I covered chemical and completed. I covered 90% of phase. And you haven't watched. So I will just cover my ionic at my own pace and make sure it's a very good topic for you guys. So you can see we are just next to the main target of the lesson. Let's do properties, types of each, examples in each case, and yeah. Okay. So equations for each theory. Equations for each theory. Equations for each theory shall be given at the learning target. At the learning target, because we have it. Eh? So when we reach that learning target of equations, I will tell you. So you people are the ones to tell me that that is Arrhenius, that is Bronsted and Lowry. Learning target. Equations for each theory shall be given at the learning target of equations. Yeah. So don't worry. But theories have definitions and equations, but we shall see the equations. Just don't worry. But just know if you don't understand the equations, they are hard. They are hard. People fail to write them. But we are going to struggle with them. So prepare your books, prepare your pens, prepare your cameras. You're going to be taking pictures and sending, just like the way we do in pure math. Provided you understand equations, at least you'll have a beginning point. You'll be writing correct expressions of K and KB. You'll be writing, you'll be doing correct calculations. But if at all you have issues with the equations, you may be a bit disturbed. So we are going to handle something about properties. Yeah, especially for the new curriculum, properties are very important. You need to know the behavioral science of acids and bases. So properties of acids. So I want answers from you people. I want properties from you people. What are the properties of acids? What are the properties of bases? No more things. I don't want you to tell me that acids are proton donors. No. Tell me the usual chemistry. because someone told us that acids usually have some kind of taste. So you could ask yourself, out of for bases, what is the usual taste? Do they have any texture or they don't? Do they have any usual smell, usual color, anything? People are quiet. Are you saying things in the chat? Should I assume that? Is it a reversible reaction? Yes, you're going to learn that water is a pure electrolyte. You're going to learn a lot of things in this topic. Acids are sour, bases are bitter, bases are slippery, acids are corrosive, change of color of stimulus, low pH, dissociate, soapy feeding, bases. People are reading, people even know the pH chart. Okay, that is good. So you people, the other thing I usually tell you, that fruits. Fruits like lemon. Hey, things like lemon. So the lemon, let me just put it here. You all know lemons, and you all know lemons are sour. Why? The biology students know that lemons have what they call citric acid. So that word acid is very important. So the sour taste comes from the fact that we are having citric acid somewhere, and that's what makes lemons sour. So you should know that. Then concerning bases, someone said bitter, which is right. So acids, sour taste. Then this side, bitter. Yeah. Then the next thing that I can talk about is the effect on litmus. You know that acids change litmus from blue to red. Then this side, it's the opposite. It's red to blue. Then other things are not so important. Others involve a lot of reactions, which reactions we always see with time. So maybe someone talked of them being corrosive, someone talked about the low pH, and all those things will come when we reach pH. Yeah. So they will come when we reach pH. But I just wanted these normal things of corrosive, what. So, provided the acid is strong, of course not all acids because they are those we use in the laboratory. So provided it's strong and the concentration is too high, they are corrosive. Then same thing this side, not all bases, but especially the strong ones. But we prefer the solutions, which we call the alkalis. So you like it or not, even these ones are highly corrosive. And etc. You just need to find time and get others. But these are not so important. They are not even part of the syllabus. But I know they are very important as we progress. Corrosive, highly corrosive, sour taste, bitter taste. So etc. you can go and find out what their pH is. You can find out the specific reactions. You can also find about electrical conductivity. Yes, you can find out, do they conduct electricity? But then we shall find this one in another topic. So realize these things come on later. Like when we reach the concept of pH, we shall bring things back. When we reach the topic of electrolytic conductivity, we shall also bring this back. So as of now, we may not need a lot of explanation about it. I just wanted you to know the normal things of corrosive, sour, bitter, and litmus. Yeah, so that is enough. So I'll go back to our learning targets and I'll tick the properties. So we are going to talk about the types of each. I told you today we are going to interact together. We are supposed to be interactive. So you're the ones who are going to formulate for me notes for this part. Because the moment we are done with the types of each and the examples, that's when we are going to handle the equations in each case, both acids and bases. You're going to learn new equations you've never heard of. And they are going to take time for you to think things are easy. They are not. There are acids you've never heard of, like phenylethanoic acid, 3-phenylpropanoic acid. There are bases you've never heard of, ethyl methylamine, the dimethylamine. All these things are supposed to be done today. But remember, you've not covered amines, so I'm supposed to first tell you something about the nomenclature of amines. Remember, you've not studied carboxylic acids. But all those things are there on the drive. But I know many of you have not visited them. So I just want you to listen carefully. So about the types, you people are going to formulate the notes for me so that we save time. So concerning the types and examples in each case, so before, I want to give examples respect, because those ones give people hard time, especially the weak ones. So, we are going to begin with acids. So let me put here the word types. You see why I always tell you people to make notes from the videos. Like for example, here I've just put ticks. Even here I just put ticks. And there is someone who is just copying and they have also just put ticks. But you will not recall those ticks after 2 weeks. You will not recall what I said. Who can tell me what I said? Where those ticks are? What did I say? If you're following. Because when I'm just saying pH with the arrow then ticks. What did I say? You see, people don't recall. Yes, Britha, what did I say?
You said we do research whether they conduct electricity or not.
Are you sure?
Yes.
Yes, Judith, what did I say?
I remember you said that we have to research about the exact pH, the range of their pH, and their electrical conductivity.
That's not what I said. You people are lying. Yes, Gladys Gift.
Peter, I said we shall cover them later when we reach pH.
Exactly. For pH, we shall cover it under the pH concept. That's what I said. Then I told you that for electrolytic conductivity, we shall cover them when we reach the topic called electrochemistry. So when you go to the drive, this electrochemistry is topic 10, but we haven't covered it. Then under pH concept is still under this very topic. You can see it here. I think you can see the word pH concept here. This one. That's what I said. But you people are just accusing me falsely. Things I have not said. Okay. So, you people, who can define for us strong acids? I didn't want to say these things. I don't know what made me write them. Who can define for us strong acids? No one? Yes, Richard. Yes, Richard?
A strong acid is one which fully ionizes and dissociates in a solution.
Is that where you stop? Is that where the definition stops?
Yeah.
Okay. When there is a strong acid, they are meaning that it is an acid, and whatever acids do, the strong acid does it strongly. Yeah. So these acids, remember, they ionize in solution to produce protons. So because it is strong, it will do the ionization strongly. And we always use completely to mean strongly. And we say that these ones completely ionize. You write in the chat what happens after it completely ionizing. So all I want is to see the word completely ionizing. Then what happens? That's what I want to see. That's what I wanted to see. Mene. Completely ionizes, and it will give us many hydrogen ions. Like that. If you don't want to use the word many hydrogen ions, and you want to look like the real A-level chemist, use a high concentration of hydrogen ions. Yeah. Hope people are aware that square brackets mean concentration in chemistry. Are people aware? Are people aware that these ones mean concentration? I taught it in chemical equilibria. You get the point? So when I put here X in chemistry, that means concentration of what? Of X. Like that. A. Now, for weak ones, for the strong ones, we've said they completely ionize. Then for the weak ones, they partially. I'm coming. I want us to go slowly. So these ones, they do the reverse. They partially what? Ionize. And then, when they do that, what happens? The hydrogen ions are few, or people say very few, people say little. So few hydrogen ions, and the concentration is low. People say very low. Just like there, they say very many, very high. But don't mind all that. So it's low concentration of hydrogen ions. The other one do it completely, then these ones do it partially. Simple as that. Now, we are defining them according to the Arrhenius theory. It is Arrhenius that talked about hydrogen ions and hydroxide ions. But now what if we want to consider Bronsted-Lowry theory, where they talk about donating and accepting protons? So my question is, if this strong acid is completely ionizing and giving us many hydrogen ions, what does that mean? That means that, remember, hydrogen ions are protons. That means it's giving us many protons. So my question is, if it's giving us many protons, does it easily donate or it hardly donates? Does it more easily donate or it less easily donates? Okay, does it find it easier to donate protons or it finds it hard? That's what I want to see. More easily, yes, more easily. Yeah, you people are very bright. Someone is saying it finds it hard. Never. No, that person is using this case is like, rich men always have a lot of money, but they don't easily give it away to the poor. Here we are talking of chemistry, not poverty. So if it's giving you so many protons, that means it can easily, okay, it finds it easy to donate because it's giving us very many in solution. So you can just say it easily donates, or the English people can try to take things personal and say more easily. Donates protons. The things I want you to learn. The things I want you to learn. Okay. You look here. So this one, because the hydrogen ions are few, hydrogen ions are protons, so the protons are few. It's giving us few protons. That means even if it's to donate, it doesn't donate well, less easily. If you don't say less easily, if you know some good English, you can just say hardly. Hardly donates protons. Yeah. That's the comparison I wanted to give you. So we are going to see the examples, but meanwhile, you first understand this. Yeah, first understand those few things. Now, immediately before we forget, let's discuss the bases straight away using the same criteria. So bases, we also have the strong and the weak. So I want someone to prepare the notes we are going to write. Hey, just following the same flow as that of bases. We shall have here bases. Yes, please.
Okay, sir, good morning.
Yes.
Okay, so for the strong bases, they completely ionize to produce many hydroxide ions.
Yes, I'm following.
Then they accept protons more easily. Yes, that's all for the strong bases.
Only that?
That's all I got.
I've not heard you talk about concentration.
So the concentration of the hydroxide ions is also high since they are many.
Talk about the weak bases and we close the deal.
So for the weak bases, the concentration is low since they produce, can I say, fewer ions? Yeah, that's it.
Okay, thank you so much. So I think he has said it all. So concerning accepting, because it's very strong, it will, of course, that is obvious. It will more easily accept. Yeah, it will find it easier to accept than the weak ones. So more easily. Hope people are taking notes. More easily. I always prefer people writing your own notes, but if you believe notes are very hard to write, and you believe you can understand these summaries I always write, you can always just print out the workbooks because I always share them. So when I share the workbook for you, just print out. I share the workbook for you, just print out. and then take to school. One is also okay. Now, concerning these ones, it is the opposite. These ones do the reverse, they do it partially. The ions they produce are very few, hydroxide ions. That means the concentration of hydroxide ions is very low. We shall need this work in buffers. You may look at these things as obvious, but when you reach buffers, that's when you accept and realize that things are not easy. So here we say less easily. You don't say less easily, you just say they hardly accept. If your English is too much. Now you people about with the examples. Examples are the hardest. Yes, and they're the ones I'm scared of most. But I'm going to first give people a chance. Thank you, Judith. I don't know why I was writing proteins instead of proton. So, you want someone who's going to give me examples of strong acids? Yes. Then I want someone who's going to give me examples of strong bases. The serious ones, you write them in the chat. Only leave your hand up if you can give me all strong acids and all strong bases at once. If you can't, you put your hand down. And if you leave it up and I choose you and you leave any strong acid, I remove you from the meeting. That is the deal. Okay. Yes, Justus. Mention all strong acids in nature and all strong bases in nature. Without those, people have already mentioned in the chat. So don't mention HCl. People only know HCl. What of other acids? Yes, Justus.
Yes, good morning, doctor. For the opportunity. The strong acids. We have hydrochloric acid, hydrobromic acid, hydroiodic acid. We have nitric acid. We have sulfuric acid. We have chloric 7 acid. Then the strong bases. We have all the hydroxide, potassium hydroxide, sodium hydroxide, barium hydroxide. Then we have also lithium hydroxide.
Which book do you read? Do you have it there? Okay, which book do you always read? Do you have it there?
I have it, but it's aside.
It's what?
It's aside, but I summarized my work.
Oh, do you have a matchbox?
Yes.
Burn it.
Okay.
So the strong bases are only 2. The strong bases are only 2 at your level. Thank God you mentioned them. And for the strong acids, we usually mainly use a few. Of course, not all. So we have the HCl, which is the hydrochloric acid. We have the sulfuric acid. We have the nitric acid. And etc. Those are the main ones. Yes, they're the main strong acids. And others. What I need you to appreciate is that these acids only work as strong when they are dilute. Only when dilute, that's when they are strong. Only when dilute. Then at your level, the strong bases are only two, that is sodium hydroxide, then potassium hydroxide. Leave other things. Why I'm using structures, there is a 5-hour lesson we had on chemical formula and chemical equations. I think they have a total of 10 hours. Those 10 hours were worth it as far as these things are concerned. So forgive me if you have issues with chemical formula. In most of the cases, I will not write the chemical names. I invested my time then. So you visit the drive and find yourself a solution. So they are basically those. I've not said that other acids are weak, but we shall mention them and see. I can give you some other strong acids. For example, the phosphoric H3PO4. Also a strong acid. Good one. But there are those acids you've been mentioning. I've been hearing them for the first time. I didn't know they are strong. But have it in mind only when what? Dilute. There is this thing I'm going to just mention and I will never maybe write it, but it's supposed to be here. You just listen to it. An acid like sulfuric acid, the moment it's concentrated, it is weak. It cannot be a strong acid. Hope you've heard, and I'm not repeating, but let me repeat once. An acid like sulfuric acid, the moment it becomes concentrated, it ceases to be a strong acid. It behaves as a weak one. You see that in organic chemistry and alcohols and phenols. So you can also visit the drive and see what exactly I mean. Okay. Now, the weak part. That's where the chemistry is. Examples, but for the weak ones. Who else can try to unmute and you're ready to say something about weak acids and weak bases? Examples. I don't want wrong answers. Yes, Mumenya, you're going to give us 5 examples in each case. 5 examples in each case.
Yes, so for the weak acids, we have carbonic acid. Then we have all organic carboxylic acids like methanoic acid, ethanoic acid, propanoic, butanoic, to mention but a few.
But there is a way you're giving me answers, and I'm starting to get worried. If you don't mind, which is your school?
The school I study from,
Yes.
St. Julian.
Okay. So examples of weak acids, we have the inorganic ones. Then the organic acids. So the inorganic acids that we have, someone may be like, doctor, what of the physical acids? Because we also have physical chemistry. That's not how things work. The compound is either organic or inorganic. So the inorganic ones, they have mentioned for us carbonic acid, which is this one. etc. But I can also add for you some other acids. the sulfonic, or what you people call sulfurous acid, that one, and others. But these ones, no one will set them for you in this topic. These are the acids. These are the acids they concentrate on. They are the game of the topic. Game, GEM. The moment you have issues with organic acids, you cannot do any calculation as far as acids are concerned in this topic. They are the ones they concentrate on. So the organic acids in chemistry, they are the ones they call the carboxylic acids. And you all know that carboxylic acids have this one as their functional group. I want you to follow. So as you give the examples of the weak acids, strictly under the organic ones, which are the carboxylic acids, you should put this in consideration. The moment whatever you're having lacks this group, then it's not the target acid, it is something else. So in organic chemistry, as you're writing any homologous series, as you're writing examples or compounds belonging to any homologous series, you should put into consideration having the functional group as part of the compound. The moment it misses, then it's not that compound. So the functional group is the identifier. So, those of you who attended the organic chemistry session with me, in the beginning, I remember telling you a lot about chemistry. Who can tell me the prefixes I talked about? Okay, who recalls what I said? Let me see if people have a good memory. Which other name did I give to carboxylic acids? You tell me. Which other name did I give to carboxylic acids? I've given you a chance to use the internet, and because I know many of you have forgotten, you check the internet and see. I've given you a chance to use the internet. What is that other name for carboxylic acids? As I draw my structures here. You people, is this the spelling of weird? Even someone who has not yet understood is going to contribute. They're like, hey, it's my time to shine. Is that the spelling of weird? Hey, what are people writing in the chat? Are you writing correct things? Alkanoic, 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 alkanoic. Yeah, that's the word. Yeah. Now, I want people to tell me. You're saying, the internet is saying alkanoic acid, which is very okay. Who recalls the four prefixes I gave you here? That in case the compound is having only one carbon, 2 carbons, 3 carbons, 4 carbons, what are the prefixes I gave you for each of that? I gave you these things when I was teaching you the introduction. We really struggled. But some of you have already forgotten the struggle. Yes, Judith.
For one carbon, it's meth.
It's meth.
The second, it's eth, prop, and but.
Now, do you remember the role of prefixes that I gave? Because now for you, you might have you may be this person who knows the prefixes, but at least I know. If you're lying to me and you never attended that class, you cannot tell me the roles of those prefixes. Who recalls the roles of these prefixes? What do they replace? Hey. Yes, Engineer Joshua, what do they replace?
Yes, good afternoon, doctor. They
You told me
replace
the
what,
answer.
doctor? They replace YL.
They replace what?
YL.
Yeah,
They are,
YA.
if it is, sorry, doctor, if it is like in myth, we add YL.
That is now you're adding. For me, I want to know, what does meth replace? What does eighth? What
Myth,
does prop? What does
they replace ALK.
Exactly, that's what I wanted. Thank you, sir. They replace alk. Just that.
Yes,
In
and
every compound, and trust me, all compounds in chemistry have this word alk. It is you who decides to call alcohols alcohols, but a student who passes organic chemistry calls them alkanols. It is you who decides to call carboxylic acids like that, but for us we call them alkanoic acids. It's you who decides to call ketones as ketones. For us we call them alkanones. And I said all that in classes. It is you who decides to call them aldehydes. For us, if we want to understand the name, we call them alkanals. Why do we prefer these names? We always want to have this alk, and understand that the prefixes, we always replace the what? The alk. That's why we always have things like methanol, ethanol. You get propanol, butanol. Ethanol, propanol, butanol, such things. That's why we always have things like ethanol, methanol, propan 1 or propan 2 or like that. Because we know this alcohol is be replaced by the prefixes, which prefixes correspond to the number of carbon atoms. If you feel like I've just confused you, visit those different classes. You will enjoy. You will enjoy. So, what is the essence of what I've just talked about in this topic? Remember, as they give you a question, to do any calculation, they use the nomenclature. So you should be knowing that when I see meth, my carboxylic acid is having only and only one carbon. When I see eth, there are only and only 2 carbons, prop and but like that. Okay. Now, why I put here, remember we are drawing acids, and acids should have only and only one carbon. So for me, I'm going to come and show the group throughout. Because I'm dealing with acids, so I know the group is supposed to be there. So even here I'll come and show the group. like that. Even here I'll come and show the group. Even here I'll come and show the group like that. So after you appreciating that we should have the functional group throughout, you ask yourself, if it is meth and meth is supposed to have one carbon, we already have the carbon, so don't add any other carbon. So you just fill this space, and you know it is always hydrogen that is always there for us. Every time we want to fill any space, hydrogen is always there for us. It always comes through. Then when you go to the eighth, we have said the carbons are supposed to be 2, and we so far have only 1. So you add that second carbon. But when you add it, it's having only 1 bond, so you have it in mind, it will need the 3. You get it? Then when you go to prop, you know the carbons are supposed to be 3, but we already have 1. So have it in mind, that very carbon in the functional group is counted. Don't think it's just there for fun, please. It's counted. To make them 3, you should add there how many? More 2 carbons like that. This one in the middle is having 2 bonds, so you make them 4. This one at the end is having only 1, so you make them 4 by adding 3. The same thing with bute. It needs 3 of them, so it needs this one, it needs this one, and this one. So this one's in the middle, we just need 2, 2, 2, 2, but this one at the end will need how many? 3. So that each carbon is happy, just like that. So when you come to have the general structures, you will have H, C, O, O, H. Then this one will be CH3. You all know that the hanging bonds mean hydrogen. Then COOH. Then this one, it will be CH3, the first one. Then the second carbon is CH2. Then the last one is COO what? OH. Like that. Then this last one, the same thing, eh? Just have CH3, CH2, CH2, then COOH, like that. So then when it comes to the naming, it is easy. For you just come here where there is alk. If it is 1 carbon, put there meth. So the name becomes what? Methanoic acid. You get the point? Methanoic acid. Come here. Carbons are 2. Remove alk and put eth. So the acid becomes ethanoic. Because we know the prefixes always replace the alk. This one, 3 prop. Put prop where there is alk, propanoic. These things look easy here, but if you don't practice, you don't get anything. So but replaces alk, then becomes butanoic. So in your free time, you add on, in your free time, you complete the table. Yeah. And I want you to go up to carbon number 6. So 5 and 6, this one is your assignment. It is not research because you just replace. You put penta and X. You draw the weird structure, you condense your name. So I told you that you're supposed to take screenshots of such assignments you post in the group so that people can see the highlights of the lesson. Yes. So that is it. So hope people now know the weak acids. They are the inorganic ones. I only gave you the nitrous, carbonic, and sulfurous. You can come and add nitrous. So nitric is NO3, nitrous is HNO2. I taught this long time in chemical formulae. Yes. Then the organic ones are the carboxylic, the alkanoic, and that's how they look like. So you should be ready for them. Now, the question is about the weak bases. Weak bases. Who can raise up their hand and tell us anything concerning examples of weak bases? I saw Charlotte on. Is Charlotte still on? Not Charlotte Charity. Not that one. There's another Charlotte. She's called Charlotte Patience. She's my student at Taiba International. I wanted her to read for me what exactly I gave them in their books. But I think she's not here. Anyone who can give us examples of weak bases? Weak bases. Yes, Justus. I think Justus has given up.
Some of the examples of weak bases.
Why you don't greet?
I'm sorry, good afternoon, doctor. Some of the examples of weak bases, we have aqueous ammonia, we have aqueous methylamine, we have hydrogen carbonate, we have ammonium hydroxide. I think that's what I have.
Oh. So you refuse to ban the book? So we have these bases, these bases of magnesium hydroxide and so on and so forth. There is that group of inorganic ones. This group was dumped long time ago. Yes, was dumped. The inorganic weak bases. The inorganic ones. It was dumped. We don't need it here. We don't need it here. So I'll put danger. Show you that I don't need them. I don't know if that is the symbol for danger. So the thing you're supposed to note, just as I want you to take back that statement. I heard you talk of ammonium hydroxide. Ammonium hydroxide does not exist. Yes. So this is the note. Aqueous ammonia. So it's aqueous ammonia. Ammonium hydroxide does not exist. Aqueous ammonia is the grand weak base. Is the grand weak base. Let me call it the great weak base. And gives rise to all amines. Hence, all amines are weak bases. Because ammonia is their father. That is it. You people first understand that ammonia, small ammonium hydroxide, that one does not exist. If you want to really write ammonia in form of a solution, it's either aqueous ammonia or ammonia solution. We are going to see that. But ammonium hydroxide does not exist. That word is not there. So ammonia as ammonia is our great weak base that we have. It is the grand, I'd called it the grand, or you can call it the great weak base. It is the one that comes first, the rest come later. And it is ammonia that gives birth or gives rise. I think let me say birth. It gives birth to all other amines. We are going to see how. It gives birth to all other amines. Is the grand weak base or the great weak base. And it gives birth to all amines. All amines. You like it or not. That means that because of genetics, because ammonia is their father, find out that they also take the father's trait, which trait being a weak base. So all amines are also weak bases. So we are just supposed to find out how are amines generated and how do they look like. I told you this is the part that is going to make the lesson long. You knowing the examples of these things. Otherwise, I could just tell you methylamine. Examples are these ones, methylamine, and then people start cramming, which I hate. I want you to understand that their father is who? Ammonia. So that means the daughters and the sons will also take on the dad's trait of being a weak base. So let's first note this and leave it. Ammonium hydroxide does not exist. Why do I even write it? Ammonium hydroxide does not exist. It doesn't. Then, what is the correct name? If you really want to mean that ammonia is acting as a base or ammonia is in solution, it is aqueous ammonia. It is aqueous ammonia or ammonia solution. You know aqueous means solution. Or aqueous ammonia, ammonia solution. If you want to know how you really write it, let me just put it here. You write ammonia like this. Then to show it is a solution or aqueous, you put aqueous in brackets like that. I don't think that is hard. You see this? Ammonia, then aqueous. That is enough to show what you mean. So now, people, the thing is, how do you create these amines they are talking about? How do you create these amines they are talking about? Now, people, I want to ask something. What is the functional group of amines? I remember teaching you that. What is the functional group of amines? What is the functional group of amines? You tell me. That's what people are saying in the chat. People, thank you for maintaining good numbers. Yes, we are about to reach the equations, which is the major thing. All people know it, amino group. Yes, thank you for that. So you people, look here. Look here. We are covering what? Amines. So we are saying that when are these amines going to be formed? And we are saying that they are formed when 1, 2, or 3. What am I saying? They are formed when 1, 2, or 3 of the hydrogens of ammonia are replaced by R. I don't know if people are getting. Remember, ammonia is like this NH3. It's having 3 hydrogens. That means you can either replace 1, you can either replace 2 of them, or you can either replace all of them, the 3, like that, like that, like that. And what do we mean by R? I've always told you. I taught you alkyl halides myself, so I'm not going to over struggle here. By R, it could be the alkyl group. So if at all you get lost somewhere here, you will have to revisit the lesson of alkyl group, where we have the methyl group. The methyl group, you know, it's like this. It can be the ethyl group. Then in this topic, they already just call it the propyl group, but it could be modified. Could be modified. So this one is CH2 CH3, like that, propyl group. This R could be the aryl group. And you people know that the aryl group, strictly, okay, it's basically the phenyl group, like that. Then the group could be a modified one, or it could be mixed. What I mean by mixed is that you can have the benzene ring, maybe with a CH3 like that, then with the bond there. You get? So that R that is replacing one or more of the hydrogens of ammonia could be the alkyl group with those examples, as you can see, methyl, ethyl, or propyl. It could be the aryl group, which is basically the phenyl group, or it could be mixed with both the benzene ring and some aliphatic chain. The other group, of course, cannot be used. You may ask yourself, so the aryl group is only one? No. You also have the naphthyl. Someone write for me the spelling of naphthyl. Naphthyl was one of the words I used to like most during my prime. During my prime as a chemistry student. Back then, 11 years ago. You write for me the spelling of naphthyl. Write for me the spelling of naphthyl in the chat, just for fun. Now you're there, there is no way you can tell AI to help you because you can't even spell it, you cannot speak because you're on Zoom and you are addicted to ChatGPT. I think you can see that you need to sit down and read books. You try to tell ChatGPT the right spelling of naphtha, you write a very funny word, it brings Napoleon. You just give up and come back to the chat and check what people are writing. Naf. It's naf. Because I've said naphthyl. Naphthyl. It doesn't have E. People are writing naphthalene. I wanted naphthyl group, just like the way you see phenyl group. Yeah. Okay, people. Let's see some of the examples. Let's see some of the examples and how we can name. So I want people to look here. Assuming this is your ammonia, I don't want you to tell me things like, but ammonia has a trigonal pyramidal shape. We are not drawing shapes. We just want to generate our amines. So assuming this H is lost and then replaced by maybe CH3. Yeah. So the moment it's replaced by CH3, do you know what is going to happen? The structure that is going to come up, it will be CH3 NH2. Someone may be like, how have you obtained that structure? You look here. The structure will be, we shall have H here, we shall have N here, we shall have H here, then we shall have CH3 here. You get? So I think you can see. If we are to condense, we can begin with the CH3 and then write the NH2. It's like the CH3 is touching. So this is the NH2. The one up here is the NH2. Then down we are having our methyl group. I think you can see. It's even very clear for it. So that's why I'm drawing it like this. So the other thing I want to tell you, that this remaining thing, the balance, this one, remember it is touching the CH3 at the other end. So that bond NH2 is what they call the amino group. Is what they call the what? The amino group. So you should understand that. Amino group, and it is the functional group of amines. Yeah, it is the functional group of amines. Just take note. Functional group of amines, but you don't need it now. All you need to know is the amino group. So let me see if we are having any serious student here. Any serious student here who can name for us this. I'm going to give you the hint here. IPAC name. I'm going to give you the simplest hint. So you people, if you really want to name that, I want you to copy. What is the hint? Copy. Copy the name. Copy the name of that, because we named it together the other time in alkyl halides, and then name this. You people don't use the internet. I want you to learn these things. Anyone? You copy the name of that and name for me that. People are trying. But trying. So this thing has two names. It's having the chloromethane name. It's having the chloromethane name. And I'm also telling you about the methyl chloride. You see, this organic chemistry is very weird. And you're going to be shocked. Yeah, and what I'm about to say is some of those things that make you a top-notch student in a branch. So remember telling you that as you're writing methyl chloride, leave some space, isn't it? Which is very okay, leave some space for methyl chloride. So I'm like, if you really want to copy, this is CH3, NH2. Why we say the chloro? Because this was the chloro group. I told you that. So this one, this is the amino group. So this one will also be amino, eh? Chloro group, amino group. So this one will also be amino. Methane. And it is one word, just like the one on top. Chloromethane, one word. So even aminomethane, one word. So, this other name, it's methyl. You like it or not, even this one will be what? Methyl. But now the other one was a chloride, this one is an amine, but this one is one word. One word. So you tell your neighbor, you close your eyes and meditate. You be like, methyl chloride is one word. But methyl chloride, there are two words, you're supposed to leave space. But methyl amine, it is strictly and strictly one word. So those who are leaving space in the chat, please, you combine it. Yes, even those that tried it, some of them it was by coincidence. But methyl chloride separate. Methyl amine, it's one word. So, for chloromethane, this is what is preferred. So they prefer chloromethane than methyl chloride. But when it comes to this, methyl amine is preferred. Please understand. Aminomethane is okay, but methyl amine is preferred. Here, methyl chloride is not okay at all. The best name is chloromethane. Yes. But they overuse these words of aminomethane and amino others. But these ones that have amine, they are the best. They are the best and they are preferred. Hope you understand. So when I ask for the IPAC name for that, I will be very happy. Be very happy if people give me methyl amine and it's one word. Methyl amine, one word and single M. Single M. The other double M is used in complexes. So if you're not talking of a complex, don't stress yourself. If what you're talking about is not a complex, don't stress yourself with double M. Okay. Now you people have taught you how these amines are. Okay. Please leave our screen. Now how can you call yourself Letecharia? It is L somewhere. But I can tell that we are of the same tribe after seeing Lechetaria. Okay. So what's next? What next? Okay, let's name these that is our money. So what if this H is removed? What if that H is removed and replaced by the CH3, CH2, then NH2? Yeah, like that. What is the name of that? Very fast. If I want you to be fast, this is the second. These ones we are going to name them separately. I've told you the name that is preferred, eh? But you're going to be giving me both. You unmute, eh? I don't want to see an answers in the chat. You unmute, you give me both names, you tell me that, doctor, this is what they prefer. So this is our ammonia, like this, like this, like this. Then this one will be like this. You give me both and tell me the one that is preferred. Because trust me, they use nomenclature in question. So if you cannot do the structure, you're gone. So what if this time round they replace these two? Yes, what if they replace these two with CH3? So there will be two of them. Then we shall have this. And I have only two to go. If it's like that. People are taking notes. Judith, you're going to name all of them, not only the first one, all of them. So I think we can start. Let's begin with this. All of them. We save time.
The two names, one of them is ethylamine and aminoethane.
Ethylamine, is it one word?
Yes.
Then the other one is amino what? Which one is preferred?
Ethylamine.
Ethylamine. We go, we proceed. Then this one, what is the first name?
Phenylamine.
Phenylamine or phenylamine. Then amino what? Phenene. Aminobenzene. If you people recall chlorobenzene and bromobenzene, aminobenzene cannot disturb you. If you recall that at one time we said chlorobenzene and aminobenzene, it shouldn't disturb you and you should be aware that it is one word. I think we even named it in the topic of benzene. That one is not my worry. So what is preferred is phenylamine. Then have it in mind that it is commonly called adenine. Aniline, commonly called aniline. Yes. So when they use aniline, that's the common word for aminobenzene, hypercally called phenylamine. Then this one,
I know only one name, and that's dimethylamine.
that's why the arrow is 1. So to be on the safe side, so just maintain our name. So dimethyl, dimethyl, like the methyl are 2. So it's dimethylamine. But for you, can't you say amine? What do you say amine every time, like a local person? So dimethylamine. So someone may be like, Doctor, what you mean this one is also an amino group? Yes. but we always use one word, only one word. These ones are also amine, so that means the amino group is there as the functional group. Just don't mind, so you just do the right thing. Then the next one, how are you naming it? Okay, you first name the F. First name F, then I name for you E.
It's propyl amine.
Propyl amine. Because of this propyl group. So it's propyl amine. But do you see that these ones are also 3 carbons? And the amino group is touching the carbon in the middle. So that's what they call isopropyl. Isopropyl amine. Isopropyl amine. Why? There are also 3 carbons, but the amino group is not at the end. It's in the middle. And the moment it's in the middle, those are what they call the isomers. So it's isopropyl amine. They will not even set it, but it is something you can brag about. You name G. Remember, we are saving time. Name G.
It has defeated me.
Okay, you name H.
H is triethyl amine.
Exactly. So this is the ethyl group, and the ethyl groups are 3. So because there are 3 triethyl, because there are 3, we shall say tri. Then because of ethyl, triethyl. So it's triethyl. One word, amine or amine, whatever you want. What can you say about that? I remember talking about it in alkyl halides. Though for us here we had Cl, but people have already forgotten. Just because for us there we had the Cl, the Br, and the I. But I talked about it in alkyl halides. But you people just have bad manners. And I also leave you and give it to you as research. I remember telling you that if you have aminobenzene, that if you have benzene and you put the amino group, it becomes aminobenzene. Then I told you, what if now I have methylbenzene and I add the amino group? What does it become? Aminomethylbenzene. Is that hard? So look for its name as an amine. You know the people have gotten it, yeah? When you get the when you get benzene alone and add the amino group, it becomes aminobenzene. So when you're having methylbenzene and then you remove one H and leave them as 2, then you bring the amino group, it will become aminomethylbenzene. So it's easy. One word, aminomethylbenzene. Now look for that, the other IPAC format that has amine. Organic chemistry doesn't change. So those are the names they'll be using in the questions. Especially the thing of dimethyl. Most people cram and be like, every time all amines are supposed to end in NH2, forgetting that there are amines like dimethylamine, which will end in just NH. Forgetting that there are those like trimethylamine or triethylamine, which will just have H. You people should understand that all amines come from ammonia. Get the point? So when they tell you something like dimethyl, means that the ammonia was like this. So when they said dimethyl, that means 2 hydrogens were replaced by methyl groups. You get the point? So the N remained with only and only one H. So it is CH3, there are two of them, then NH, just like that. When they say try means that all of them have been replaced. So this N will be alone. That's why you're seeing trimethylamine like this. 3 with only N. Because the 3 means that all the 3 hydrogens were replaced by the ethyl groups. Something I began with. So trust me, if you cannot name amines correctly, you cannot write the structures correctly. And because you can't write the structures correctly, even the equations, you can't pass them. And the equations are the easiest. Very easy. Very easy. You just need to be understanding the definitions. So I want someone who has been writing my notes, remind us of what Arrhenius said concerning the acids and bases. Remind us about what exactly Arrhenius said. So to do with the types and examples, I think you've seen, you've learned a lot of things. You people, I've covered 2 topics today. I've covered lesson 1 of carboxylic acids, which we already have on the drive, and lesson 1 of amines, which we already have on the drive, because I've been struggling with nomenclature. Yes, and examples in what? In each case, we are done. Research and assignment, you already have some, and by the end, we shall have ticks. The next stop is just stated. That one has no rocket science. That means the basic guys here, equations, and that's what we are going to handle. If you understand the equations, you'll be the best chemistry student in your area, because you'll be talking of things people don't understand. You even give them work. You'd be like, I'm going to do that of methylamine and ethyl, you do that of aminomethylbenzene and aniline. Or you leave. You'd be like, for acids, I'm going to do for you propanoic and butanoic, then I'll give you others. I'll give you 3 phenyl propanoic and one phenyl butanoic. Just showing off, even when you don't understand anything. But you just put situations up. So, someone raise up your hand and remind me of what Arrhenius said about acids and bases. That's what I want to hear, because equations are going to begin. Equations are going to begin. So I want people to type in the chat, ready for equations, ready for equations, as umama tells us something. I want people to tell me, ready for equations, ready for equations, ready for equations. The equations we are going to write, you have never seen them. For you may think we are going to do weird things, but they are serious. Equations of ionization. And we are going to begin with acids. Then the first one, strong acids, just equations. Yes, Safiat.
Thank you, sir. Good afternoon, sir, and good afternoon to all of you. Sir, I remember that we say that for the acids, for them, they ionize on dissolving in water to produce hydrogen ions. Then with bases, they ionize on dissolving in water to produce hydroxide ions.
Who said that?
Sir, you told us.
Whose theory was it?
It was that theory of
I want you to say that full name.
Okay.
Hey, for me, I have experience. I know. People, someone is always like, after all, I can spell. I'm not going to stress myself. Yes, it is very hard. Ah, okay. So the name is Arrhenius, eh? ARRH and what proceeds. So for him, he just talked about the acid ionizing to produce. I think I'm going to get a better zoom such that there is no option of muting yourself. Since it's me who gives you the permission to unmute, when I ask you to unmute, it's me to mute you, and you cannot leave the meeting. Those things of disappearing are not going to work anymore. Okay. Now, concerning the strong acids, I gave you the examples. Yes, so I'm going to just be pasting things. Yeah, pasting things. So the very first thing, I want you to look here. I want you to look here. An acid like HCl, aqueous. I don't know if people are aware that even tonight we have ionic equilibria. We are beginning calculations, calculating until further notice. So we all know that these ones completely ionize. So because they completely ionize, we shall use a full arrow. These ones completely ionize. So because they completely ionize, we shall use that, the full arrow. Yeah. So I'm going to come. So the full arrow meaning completely. So after that, what do I have? You people know that we get H plus. I taught you this when I was teaching you the equations of period 3 elements with hydrochloric acid, that it has two parts, that one and this. That is the equation most of you know. And it is very okay because no one will examine it. Very okay. And all of you know that. I remember telling you that if this is HCl, there is a boundary line here. You know H is supposed to be a plus, this is a negative, and those are the two ions, not forgetting the aqueous. So well balanced, the formula correct, you have correct physical states, you get your 1.5 marks. You see that? Very easy to get. Very easy to get. Now, because we are just producing the hydrogen ions, these ones, this is where Arrhenius comes in. So I told you that we shall talk about the equations of the theories here. So that was Arrhenius. Yeah, because we are just producing. This one was Arrhenius. So when I do that, I mean Arrhenius. ARR. Then Bronsted Lorry, I'll put BL. That is Arrhenius. Now there is another option. There's another option. I want you to listen carefully. Who knows the structure of water? Who knows the structure of water? Okay, I just want you to reply to me this. You people, those who know the structure of water, does it have a lone pair of electrons or lone pairs of electrons anywhere within its structure? Does it have lone pairs anywhere? Does it have lone pairs anywhere? Does it have lone pairs anywhere? That's what I want to see in the chart. Then for me, I will draw them on my two lone pairs on O. Very good. You people, if we keep serious like this, we shall pass chemistry. Yeah. Okay. Structure of water. So structure of water, we have our O. I think we are supposed to find some time and also have a class on drawing these shapes because they are the easiest, but I see people crying, shapes. Yes. And you know the name is V-shaped or the bend shape, like that. So for me, I'm interested in, this is what I'm interested in. So for me, in whatever we are going to do, I'm going to condense it. I think we did that in alkenes. And I told you that for purposes of learning or purposes of mechanisms, we always compress this. How do we compress? Said we always compress this. And how we write the O? Then we write the 2 hydrogens, that is H2. You get? Then we expose only one lone pair. Only one lone pair like that, because it's what we are interested in. It's what we are interested in, isn't it? You leave the, yes, there are two, but first we are interested in one. So I want people to first appreciate and befriend the fact that water is also the same as this. Though they may look different, but I've just tried to use the mirror image. Okay, so you people know that these are electrons, and they are negatively charged. So these ones are electrons. So electrons, they are negatively charged. Since they are negatively charged, what does that mean? That means that they can attract positive. Because they are negative, that means that they can attract what? Positive. I want you to listen. That is the structure of water. And if I'm to compress it for my own benefit, that's how I prefer. And because these electrons are negatively charged, I'm like, they can attract a positive. And we are talking, so I want to ask people a certain question. Remember, we always have, okay, when I said dilute HCl, what do I mean? Remember, we say these are strong acids and they work when they are dilute. Someone tell me, when I say dilute HCl, am I right to say that it is a combination of HCl and water? Am I right? Because I don't think without water I would have this word dilute. It's like we're having the HCl, the acid, but of course there is some what? There is some water, isn't it? Remember, these acids are strong when they are dilute. So don't forget that these acids are very strong when what? And even told you a secret of a certain acid that you know that is strong, but the moment you make it concentrated, it will behave as weak. Now, my question is one. If at all we have it here, we're having the HCl. Are you listening? This HCl is aqueous. You all know it's aqueous. And it's giving us H plus, aqueous plus Cl, aqueous, like that. But remember, within this very thing, we have their water. Have their water. I'm going to just draw a few. Yes, we're going to just draw a few. But there are so many. And you people are telling me that that's what they call now a combination of dilute what? HCl. That the HCl is there, yes, and it's ionizing as it's supposed to be. But then the water is also present. So this water can do something that we are going to look at. Sorry about that. Sorry. So I'd explained everything, and I told you that this is how water looks like. This is where we are. And I told you that these ones are lone pairs of electrons, and we said they are negative. So because they are negative, they can attract what? Positive. Hope you had. Now, I was still telling you that when they said dilute HCl, What do they mean? They mean that the HCl is there, yes, and it's water that is making it aqueous, but also the dilute part means that water is there. Shouldn't forget it. So if we are having a bowl, this, I hate these things that confuse me. If we're having the HCl aqueous and it's giving us the H plus, of course aqueous, and the Cl minus, of course aqueous. But we are saying in the same beaker there is some water because our acid is what? Is dilute. And I said I would draw a few, 3 of them only. Not so. Now my question is, according to the chemistry I've just explained, do you think this water can attract this H? Do you think there can be any attraction between the two? Or of this one and this one, which one do you think water will attract and why? So I want someone who is following to give me the reason. Give me the answer and why. What is the question? I'm asking. The acid has ionized as we expect it, according to who? To Arrhenius, as we've said. Because for him, he just said, produce hydrogen ions in solution and that is done. Arrhenius. But I'm saying, this water that you guys are telling me that because it's dilute, so there is some water in the same beaker. So, of these two ions that have been formed, the hydrogen ions and the chloride ions, which ions can water attract and why? And which ones does water repel and why? That's what I want to know before I can tell you my word. Yes, let me hear from Engineer Josh. You have to
Yes,
tell me the
doctor.
reasons why. Mm-hmm.
Water can attract the hydrogen ions because water
Mm-hmm.
has oxygen
Mm-hmm.
with lone pairs, and
Mm-hmm.
those lone pairs have electrons that are negatively charged,
Mm-hmm.
so they can attract the positive ions on the hydrogen ion.
Very good. Perfect. Then the other chloride ions will be repelled. There will be nothing because they are negative, even what has the electrons which are negative, so they cannot be an attraction. So that is just perfect. And thank you for that statement. So people are saying that that means, I don't know, okay, this is what we are saying, that this water can interact. What we are saying, that these two can interact. That's what people are saying. But now when they interact, we need to know what is going to happen. What is going to happen? And that's what I want to do for you here. And you learn. So, you all know that your water is like this. There is that lone pair. So when it attacks the H plus like that, what do we come up with? Come up with OH with a 3 like that. But you people should tell me, is everything normal? Does OH3 exist? Does OH3 exist? Or there is something missing? Or there is something missing? I think let me draw a better image here so that people can see something. When those two interact, I want you to look here. Let me remove this Arrhenius guy. So this is what we are saying. When those two interact, what happens? What happens is this. We are having the water like that with those lone pairs, isn't it? And we are like, it can attract the H plus. You get the point? That's what we are saying. That's how the water looks like. Now, when that happens, you all know we are going to have our O. It will have the H, it will have the H, and it will have the H. What do you think is happening? Are people giving me answers in the chat? Positive sign, portion will be lost. Missing, it exists, something is missing, no, a plus is missing on oxygen. Exactly. I remember training you very well, and I told you that in chemistry, so we said that strong acids, strictly and strictly, they should be what? Dilute. So I remember telling you that in chemistry, the moment you get less or excess bonds, in most of the cases, something becomes uncomfortable, it becomes unstable. I told you this in introduction. And when something becomes unstable in chemistry, how do we show that it's a casualty? We give it a positive, as simple as that. So whatever has just happened, the oxygen has gotten a third bond. And oxygen is only stable with 3 bonds, making those bonds excess. So the atom is unstable. How do we show that it is unhappy, uncomfortable? We give it a plus. So we should put a plus here. Now, as usual, we are people who are good at condensing. When we condense, we come up with such a structure. After condensing, we may decide to rearrange, putting it in the format like that of water. And when we rearrange, we shall come up with something like this. I don't know if we are at the same page. I don't know if we are at the same page. I don't know if we are at the same page. I don't know if we are at the same page. So I want people to tell me in the chat, what is the name of this thing that has been formed? I know there are those who are going to learn it for the first time. That is okay. But also appreciate those who have an idea. You can tell me. Now, let me give you the name first. Then I ask you what I want to ask. So the name or the names of H3 plus. They are easy. They are easy. I want someone to unmute. We name them together. I only want to give you the first one, then you give me the last 3. But we are going to do them together. Don't worry. It's not you who is going to give me them, but I'm going to guide you. So anyone who would want to teach with me the names of that ion, so that you also leave a memory at Science Scholars Academy. Yes, just us. Unmute.
Yes, good afternoon, doctor.
So the first name is hydroxonium ion. Hydroxonium ion. That is one name, and it is correct. Very correct. Another name is here. You read it for me.
Donium.
Oxonium. Oxonium ion, and it is very right. Another name is here. You're going to read it for me. Another name is here. Read it.
Hydronium.
Hydronium. Thank you, sir. You can mute.
Welcome.
Hydronium ion. So for you, just choose the name that you want. But the first one is commonest. Because there are 3, so we use the commonest. So the commonest is this one, hydroxonium ion. But if you want to have the 3, they are there. Hydro cusonium or cusonium hydronium. That is a set of the names of that thing. So I want to shock you again. So look here. Alternative 1. Remember, you were trying to show the equation of ionization of HCl. So alternative 1. Alternative 1 you have, and it's the one of Arrhenius, isn't it? Just getting the HCl and trying to break it. Alternative 1, simply get the HCl, get the ions H plus, aqueous, Cl. You only need to understand this, then the rest will be very clear. So you get your marks. We said this one is Arrhenius. Then alternative 2 is what we have just discussed. Alternative 2 is what I've just discussed. And what has it been? We want the HCl, to interact with water, a liquid. Never forget the full arrow. Never forget the full arrow. Now here what we said is that this HCl literally can produce the H plus, sorry, the Cl minus and the H plus. Isn't it what we said? And then what did we add on? We were like, this water that is actually part of the solution, it can do something. And what was that? We said that this one can be attacked by this water. And when it attacks that water, we have realized that we are going to come up with something like this, the H3 with a plus on O, then aqueous, and then this one is not attracted by anyone. As simple as that. So the Cl minus is part of the products. But this H plus, that H plus is taken by water for reasons you know well. But the Cl minus is ignored. So it will become part of the products like that. And then this is the equation of a real A-level student. The Arrhenius is easy. The Arrhenius is for all level. Anyone can write it. But when you look at when you look at what is happening here, this one is our acid. You get the HCl is our acid. And it's like it has donated a proton to water. You get? Donates the proton to water. I don't know if people are seeing that. Do you see that? That the acid got the proton, but it donated it to water to form the hydroxonium ion. So don't be surprised when I tell you that this equation is the one of the Bronsted-Lowry, because it is Bronsted-Lowry that talks about the acids being proton donors. So there are two alternatives. Either Arrhenius directly from the ions just split, or Bronsted-Lowry, which talks about donating protons. But who is going to accept the donated proton? Water. Where is that water? It's present in the dilute acid. And what happens when water accepts that proton? When water gets in touch with H plus, we form the hydroxonium, and I've explained how. So what happens to the Cl? It is ignored. Why? For it cannot be attracted by the water, because it's negatively charged. And the lone pairs of electrons on the oxygen atom of water are also negatively charged. So it will just have to bear the situation and become part of the products. So the first equation of Arrhenius is okay, but I want you to be good students and write that of Bronsted-Lowry. No need to recall whose equation is which one. Just understand we have alternative 1 and alternative 2. And alternative 2 simply involves water. You get? No need of you remembering that this is Arrhenius, this is Bronsted, but if you can recall, well and good. But I just want you to understand one thing, that alternative 1 is direct ionization. Direct ionization. You're just doing it directly. Then you recall that for alternative 2, this one involves water. Then after you understanding that it's direct ionization, so you don't expect anything like hydroxonium. So since this one is direct, it gives you the protons directly there and then. And since this one involves water, the H plus that has been formed will be used, and we end up forming the hydroxonium. I don't know. You people tell me about both alternatives. You either tell me alternative 1 only is okay. Okay, you either say alternative 1 not okay, alternative 2 not okay, or both are okay, or both not okay. The moment you say both are not okay, you leave this lesson, change combination. Because now the lesson is done. This is the hardest part of today's session. The hardest part. The rest of the things are not hard. Especially alternative 2, because you're seeing the equation for the first time in history. But I've tried to say something about it. So I don't know if we are at the same page with members on. Now get your books and everything ready. Okay, people are saying both are okay. No problem. No problem. Now, you look here. You look at this one. Part B, sulfuric acid. So when I talk of sulfuric acid, it will be like this. And we expect it full arrow. Full arrow. Full arrow. Yes. So because of the H2 to give us 2 hydrogen ions, 2 of them. And then the sulfate ions. Hope you people know that equation. That is alternative 1. And we have that full arrow. So it's what? It's correct, 1.5. Alternative 1. Then alternative 2, that one involves water. So it is H2 SO4 aqueous plus water, liquid, the arrow like that. So we all know this one has 2 of them. It's having the sulfate ion, which is going to be ignored for reasons you know. The sulfate ion is like that. I explained everything long time. Then we are having 2 of them like that. So this one is very clear. Since these ones are even 2 protons, they will even be picked by 2 molecules of water. So trust me, as you balance, it 2 must be there. And because we are calling for 2 molecules of water, even the hydroxonium will be 2 of them like this. You will see everything coming out finally. Aqueous plus the sulfate ions. They have nothing else other than agreeing to be part of the products like that. And then that is the answer. So afterwards, you remove these ones down. Remove these ones down. Otherwise, here where we are just forming the protons, sorry, we are forming hydrogen ions in solution, that is Arrhenius. That is what? Arrhenius. Here where the acid is donating the proton to water, that's why they call the Bronsted who? Lorry. Yeah. Then I want you people to do for me. So if the balancing is disturbing you, you first don't balance. You first do the normal ones. Then you balance later on. It's not a big deal. So you people, you're the ones doing nitric acid. So this is an in-class assignment. Yes, Umma. Yes, Umma. So you
Thank
people,
you so
you're
much,
doing...
sir, for the opportunity. Excuse me, sir.
Yes, yes, yes.
Excuse me, sir.
Yes, you're excused.
Thank you so much, sir, for the opportunity. Now, where I'm stuck is that initially you told us that water is neutral.
I say that water has a neutral pH.
Now, why is it that
Here it's
it gains
accepting a
that
proton, so
proton?
it's acting as a base.
Okay.
Yes, so, but we shall see that later on in the pH. Right now, you just look at the acid. The acid is donating a proton, and the only person there to accept it is water. So we don't concentrate on the water. Concentrate on the fact that the acid is donating it to water, and water is becoming hydroxonium ion. That is enough. Okay, so that acid, you all know it's nitric acid. So either you raise up your hand and you spell the equation of alternative 1, you can just spell it. And you also spell that of alternative 2, we go to the next thing. Or you write it on paper and send the images. I just want to see like 2 images only. 2 images only. 2 images only. Because I want us to go to weak ones. Yeah, the weak ones are the most important ones. Yeah. Anyone who is done? Okay, we all know water is a liquid and the rest are aqueous. So you can just write it in the chat. I can understand it. But you send a message with both alternatives. People are quiet. Let me hope people are doing the work. Now some of you are good at, when I give an assignment, you go to TikTok. Then you come back and see what the correct answers are. Then you be like, those ones I could do. So no one can spell the equations. Just spelling. Yes, Thelma.
The first equation is HNO3 in aqueous, giving us H plus
Giving us is wrong. Which arrow is there? Partial arrow, full arrow?
full arrow.
Now continue. Full arrow.
Full arrow, H plus. Yes.
H plus only. You don't have the physical state. Please spell these things correctly.
H plus in aqueous.
Plus.
Plus NO 3 negative aqueous.
Aqueous. Then alternative 2, you spell it.
Alternative 2 is HNO3 aqueous plus H2O liquid, full arrow, H3O plus aqueous plus NO3 negative aqueous.
Very good. Now spell it again, but using words. You'd be like nitric acid aqueous, full arrow, this aqueous. Use the names of those things. Alternative 1.
Nitric acid aqueous, full arrow, hydrogen ions aqueous, nitrate ions aqueous,
Very good. Then alternative 2. Hope people are listening.
nitric acid aqueous, plus water liquid, full halo, hydroxonium aqueous,
Hydroxonium ion.
hydroxonium ion aqueous, nitrate ion aqueous.
Thank you so much. That is it. She has passed. It's only a poor handwriting that can maybe put her off. But as far as the spelling is concerned, she's right. You people, let us go to weak acids very fast. Very fast. The bases are easy. Weak acids. So these ones, you all know they partially ionize. So because they partially ionize, that means we shall use what? Partial arrows. So say bye-bye to full arrows until further notice. So I gave you examples of weak acids. I'm going to first do for you the inorganic ones. Yes, I'm going to first do for you the inorganic ones. Yeah. I'm only going to do, you do carbonic. Let me just do maybe nitrous. So those things are not supposed to touch. H is not supposed to touch any. Should be neat. So Roman 1, I will do nitrous. Alternative 1. Partial arrows. Don't forget. And it is direct. You get your H plus. Aqueous and the nitrite. This time round they are called nitrite ions like that. Aqueous. That is Arrhenius. Then if at all we need to donate the proton to the water present in the dilute acid, so alternative 2, it involves water. Like this. And you all know water peaks. Remember this one produces what? The nitrate and the H plus. So this plus is donated to water. And when water picks it up, that's why we get the oxonium ion, hydronium ion, hydroxonium ion. Not forgetting it's what? It's aqueous. Then the nitrite ion is ignored for reasons you know and not picked by anyone. Yes. So this first equation is very okay, but I would want a serious A-level student. Show people that you are top-notch, extraordinary. You write this one over hydroxonium, but both are okay. We shall see it in calculations. Yes, we shall see it in calculation. Things don't change. So the tasks you have, carbonic, then sulfurous, carbonic, sulfurous. You handle those ones, and make sure I use both alternatives. So I'll be happy to see these equations being posted in the discussion groups. Yes. Hope there is someone who is taking such tasks and posting in the discussion group to show people highlights of the classes. So both alternatives, I'll want to see them. Yeah, both alternatives. Okay. Now, I want to talk about part 2 for the organic acids. Those have been the inorganic ones. Because those ones also disturb people. And I told you it is these ones they examine, so you have to listen carefully. So if you recall our table where we were naming them from, you realize that their general structure, so general structure, the general structure of those organic acids is, realized it was like this. And I remember telling you that this R can be a lot of things. They can decide to make it what? H. It can be any alkyl group, you know them. Then you all know it can be aryl, you know what I mean, and it can be mixed. You also know what I mean by all this. I try to brief you. If it's not hydrogen, methyl, ethyl, propyl, butyl, aryl, phenyl, mixed, methyl, phenyl, like that. So let's try to. So how do they ionize? So how does ionization happen? So how does ionization happen? It's so simple. These are acids, they must donate. They must produce what? H plus, the hydrogen ions, of which, you know, that's what they call a proton. So I'm like, they must donate a proton because they're acids. So how does ionization happen? This is how it happens. So as usual, you people know what we call a boundary line. So this is where the boundary line is drawn. Yeah. Hope you people understand. So this H is what will go off as our proton, and this balance will be left as a negative. You get the point? As simple as that. Nothing much. So with organic acids, they are the easiest. When they give it to you like this, you just do your best. Put their aqueous. Put their what? Aqueous. Then know where the boundary line goes. Because this is an organic acid, it is weak. And you know where the boundary line is. So you come and draw the COO. Don't forget the minus. You put what? Aqueous. Then you bring your proton H plus. Also what? Aqueous. Simple as that. Then you get your marks. All of them. You don't get half marks even if you are short. They'll give you all your marks. That is alternative one, where direct ionization is happening. And you can see we are using partial arrows because the organic acid is a weak one. Period. So I expect you to write all the rest. So alternative one, that is Arrhenius. Arrhenius. Now what if we want to do something about Bronsted-Lowry? But it's not a must for you to know those things of Bronsted-Lowry and Arrhenius. For me, they are just my things. I just like them. Now, how will the equation be? I will have my RCOH. So I'll have my R, have my COOH, of course, aqueous. Then I'm supposed to bring my water like this. You know, if people are following liquid. Partial arrows because the acid is a weak one. So I know there is this Chi ion, the Chi balance. Then I also have my proton H plus. Of course, you know where the boundary line is. So this one is donated to this water. And that's where Bronsted-Lowry comes in. And when water accepts that proton, it becomes hydroxonium like this. Aqueous plus. The other Chi ion, it's negative, so it will be ignored. So the first one is very okay. And it makes calculation simpler. But also have in mind this, don't forget this. Those who really want to know how this one looks like, I think I have been telling you for some good time that the carboxylic acid is like this. The carbon is there. One of the oxygens is what? Doubly bonded to the carbon, then the other one is singly bonded and it's completed as OH. That's how things look like. So if it's that iron, you simply remove this H and put what? The negative on top. But the rule is simple. One oxygen is doubly bonded, the other is singly bonded. Just for those who want to show it, but this is physical chemistry. You may not stress yourself with exposing those bonds. So you tell me that both alternatives are okay even for the organic acids, and you've learned how the splitting happens. Is part 2 for organic acids okay? Should I give you the acids, you write the equations on your own? You spell them. We are going to just spell. It's all about knowing how to spell, provided you know the structure of the acid. So I'm going to be writing the names of the acids alone. You raise up your hand, you spell the structure of the acid, you spell both equations. So I want only 3 people. 3 people who are ready, raise up your hands. Raise up your hand. I want only 3. So when you see 3 people, don't raise up your hand. 3 people only. You spell the name of the structure of the acid. I thought people would be yearning for the positions. Let me first read the comments. Are people lost? Has anyone been left behind? You people, only one person is ready. I've said what I'm going to be putting here are the names of the acid. For example, Breather is going to do methanoic. So what do I expect Breather to do? To first tell us the structure of methanoic acid. After giving us the structure, she now gives us the 2 equations. That's what I want. Then the next person will do ethanoic. So I think Breather first, then Gladys Gift next. Yes, Breather. Someone, so for me, I'm going to do the third. Yes, Breather.
The structure of ethanoic acid is HCOOH.
Correct. What is alternative 1? You spell it very fast.
You first write that structure, then the half arrows,
They are called partial arrows.
the partial arrows.
Mm.
Then it's HCOO, negative on top of that last O, aqueous state, plus the hydrogen ion, aqueous state.
Very good. Then the second alternative, you don't write both in an exam. You choose one.
Or HCOOH, aqueous plus water. Then it gives you the H3O, positive on top of O, in aqueous state, plus C plus HCOO, negative on top of the last O, aqueous state.
Thank you so much. I think you can see. They're the same thing. This is the same thing as what we have been having before. Just because we have removed the H and we removed the R and put H, because I told you that R can be replaced with anything. So Gladys Gift,
So the structure of ethanoic acid is CH3COOH.
Alternative 1.
So for alternative 1 to be
CH3, COOH, which is in aqueous state. Then we have the partial arrows to form the CH3, COO, then a negative on the last O. Aqueous plus the H plus aqueous. Then for the
Very good.
second O,
Mhm.
CH3,
Do you write
COO.
do you write both answers in the paper or you choose one?
Choose one.
We proceed.
Aqueous plus water, H2O liquid. The partial arrows giving H3O plus.
Yeah. But you can even bring that one last, whichever you want. You can even say, this one is ignored. Yes, what you're saying is okay, but I'm showing you the liberty you have. You can even decide to bring the hydroxonium later. It's not that every time it must come first. Yeah, just do what you want. So thank you for that. Thank you, people. I don't know if you're following, but thank you, Gladys and Bitha, for representing your friends. So I want those who are saying first both, because I believe as I was writing, you first tried it out on your own. But if you're just copying these answers directly from the board, that's not good at all, and I'm not happy with you. So people, have you passed both? Because now I want to talk about benzoic acid. And benzoic acid is mine. If you are not told that the acid is either weak or strong, how do you notice that one is weak or strong? Someone answer that person. Because I tried my level best to rectify that. Or someone can request I unmute you, you raise up your hand, you give that person content. So people who missed my lesson of benzene, you're going to struggle with benzoic acid. You're going to struggle with benzoic acid. But we are going to try our level best. We are going to try. So you people look here. Benzene as benzene is like this. Like that. That's the benzene. So if we are to expose, what shall we have? Shall have the carbon, 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 like that. We are exposing everything. Put that here, and put this here. I want you to follow. We are exposing now everything. When you look at each of those carbons, this is still benzene. We have just exposed it. When you look at each of those carbons, it's having 3 bonds, not so? 1 on one side and 2 on the other side. That means each carbon needs only 1 bond to be happy. So that means this one just needs 1 bond to be happy, 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 just needs 1 bond to be happy. People, let me tell you this. What I'm supposed to do is to just give you the structure of benzoic acid, and then we write the equation and we div. But I know what I'm going to do now is going to help at least someone. And I want you to be forever grateful students of chemistry. So when you know the structure of benzoic acid, don't look at this as wasting time. Just know this will help someone who will listen to this in the future. Someone who will watch this before they watch benzene. So you're supposed to be patient with my lessons. That's when I tell you. Someone yesterday was complaining, why do you teach up to 2 a.m.? I told them, can I refund? because that's what we have been doing for years and it's what has helped students. So when you come and you want to stop us from having long lessons of 5 to 6 hours, then there you're just being a destiny destroyer. So appreciate, endure, persevere. Okay, so we are having here H, we're 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 having here H. That's why I always advise people that if you realize what they are going to teach you, no, you wait for the recording. When the recording comes, you go to the drive, watch it at a speed of times 2. That means if we had a lesson of 6 hours for you, you'll have it in 3 hours. And pray to God you benefit from such a speed. Okay, now, when I remove this H, I remember telling you this in benzene, and we replace it with this because we want to form the acid. Yeah? So when it's just here after exposing, you can see that the carbons are what? Are 6, even the hydrogens are 6. So this is the benzene, the real benzene. So I'm like, what if this one is removed and replaced? So we are like H removed and it is replaced by what? By this. So you all know that what structure comes up? This is what I want you to understand. You people, the moment you remove one H, the carbons have remained 6, but now the hydrogens of benzene are 5. You get? The 6th has been removed and replaced by this. I don't know if people get that structure. I don't know if people get the structure. Do people get this structure? Benzene is C6, H6, as you can see after exposure. But I'm like, what if we remove that H and we replace it with this? And it's what is here. That benzene has been C6H6. But we are removing one hydrogen and leaving this one as H5. And that one hydrogen we are removing, we are replacing it with the carboxyl group so that we come up with the acid we want. So you people, are you okay with that structure? Are you okay with that structure? Are you okay with that structure? And you people are quiet. You people, do you get that structure? Because it's what we are going to be using throughout. Okay. So, that's the structure. So that's the structure used. That is the structure used. That is the structure used in equations and calculations. That is it. It is preferred. Let me use preferred because when I say use, people may be like, hey, what you mean the other one is wrong? It's not wrong. But this one is what? Is preferred. So I've not said the other one is wrong, but this one is preferred. Why is the other one hectic? Because it's not that every time you're supposed to draw the ring, and people have issues with the ring. But if I told you can be drawing a very good structure like that of mine, you can use it. But students usually find hard time with this. But it is easy. But remember, we are going to be doing calculations. So for us, we are going to have both, but I've just advised you. But that linear structure is the one that is better. That linear structure is better than anything else. You get the point? Now, I want people to help me condense this. What of this one? What if it's like this? How can you show it? Let me give you two options. Or let me just teach you what is supposed to be done. For you just get this benzene ring alone. The benzene ring means the carbons are 6. The hydrogens are no longer 6. Why? One hydrogen has been replaced by this. So you're supposed to write H5. Then you write this one besides. Hope you people get me. Most of you always want to combine and smanya say C7. That is wrong. You're supposed to show this one alone because in actual sense it is the phenyl group. Get the point? Hey. Remember, the phenyl group has lost the hydrogen and it's looking for anything else that can occupy the position of the hydrogen. So in whatever you're doing, always leave whatever is outside the ring on its own. For you, just make sure you show the C6H5. Don't say C7H7, then you show the carbox. That is wrong. This one must be on its own. Even the phenyl group must be on its own. A simple question. Do people understand when I say that the phenyl group is C6H5? Do you get it? Do you get it when I say the phenyl group is the C6H5? Because that is the turning point of everything. Okay, that is good. That is good if you get it. That is good. So that's what I mean. Yeah, that's what I mean. That's what I mean. So I think we can now write the equation. We can now write the equation. We can now write the equation. So the equations, let's first handle case 1, then we do both alternatives. So case 1 is where I use the structure. It's not wrong, but the other one is just preferred. So you do like that neatly, then you put aqueous here. Are you seeing where I'm putting aqueous? Some of you come and put it here. That is wrong. It looks weird. You're supposed to put it here somewhere. You're supposed to put it somewhere down. Then you say plus. Okay, let's use the first one of direct. This one that is direct. Hope you know why these ones are partial arrows. Now, those of you who read textbooks and those of you who attended my lessons of carboxylic acids, I remember telling you that strictly this benzoic acid is a solid. But remember, it is ionizing in water, eh? So the benefit of doubt may go to you when you put aqueous. Benzoic acid is a solid at room temperature. In its free time, it's a solid. So putting there aqueous, we are just respecting the topic. But when you come across this statement, don't be confused. So you know what happens? So the whole of this is Yochi R up to this point. So you write the COO and the negative goes on the last O. Then you come somewhere here down and you put the aqueous. Then your H. Some of you always want to make the H very big. You make it small. Some of you force things. You want it to be the same height with the benzene ring or the benzoic acid. No, just write, just be you. And that is very correct, the direct one. So alternative 2, same thing. These things don't change. These things don't change. So alternative 2, we are going to have the benzoic acid. I told you that alternative 2 involves water. So come and place the aqueous strategically, then bring your water. So this time round, we are not going to leave the proton naked. It will be picked up by the water. So I'll have the water, then the liquid. Don't forget the partial arrows. So I said, you people are used to beginning with the hydroxonium ion there, which is very okay. But you can have the Chi ion first. About how those ions are formed, it shouldn't bother you meanwhile, but we shall see as we progress. But there's students who are so serious and really want to know everything. It's called the benzoate. The others are called the methanoate, propanoate, isopropanoate, and so many others. So this one is the ion again. But this time round, we cannot generate the proton alone. Water picks it up and we get the hydroxonium, oxonium, or the hydronium ion. H3O plus, like that. That's how it's supposed to look like. You get it? So the next one is going to be the other format that is better. Someone else is going to spell it. So raise up your hand. I ask you to unmute. Anyone who is ready to use the other option, the one that is preferred in an exam. Otherwise, you can see that the general trend of how they are supposed to be written is not changing. RCOOH is the same throughout. Identify the boundary line, negative this side of the ion, positive this side for the proton. Period. Lastly is case 2, the case that is molecular, that linear structure. So he is ready to spell it. Case 2 where we are going to use C6. Yes, danger. Unmute and spell.
It's C6
Hey, for you, don't
H5.
greet. You greet me at least.
Good afternoon, teacher.
Doctor, not teacher.
Okay, good afternoon, doctor.
You
It's
spell.
C6
C6,
H5
H5,
OH OOH. Then the
yes.
partial arrows,
Why are they partial, not full arrows?
because it's a weak acid.
Very good girl.
So we are getting C6 H5 O, another O with a negative, which is the ion.
Exactly, aqueous. Then the last one
Plus hydrogen.
with the plus on top, not so?
It's just an aqueous. The second one is
Alternative
C6
2.
H5 OOH, which is aqueous, plus water, which is a liquid.
You spell, I'm listening. For me, I will write.
Yes, partial fractions. Partial equation, partial arrows giving us C6 H2 O with a negative, and then plus the oxonium ion, which is H3 O plus, which is an aqueous.
Very good. Very good. Have you just learned this today?
Yes.
Hey, that is good. You should go back and practice again so that they become part of you. And this is what they usually examine. Aqueous plus the hydroxonium. Yeah, very good. So the person is called Danger. You ask her for her WhatsApp number. Ask her for the WhatsApp number. You inbox her. I told you yesterday that you should take the Zoom chat very serious. Yes, because there are people, I told you just 3 days back, they had a wedding and they confessed they were like, we found each other in Dr. Utaya's Zoom section, the Zoom chat. Someone was like, hi, then share your WhatsApp number. They became best friends, and just like that, 3 days back, they got married, even before their tutor. So take the Zoom chat serious. So in case you've been confused, tell Danger, give me your WhatsApp, disturb after the classes. Maybe she could become your business partner, your best friend, and anything. So, what I'm waiting to see in the chat is that case 1 and 2 okay. Case 1 and 2 okay. Take a screenshot, have it as your updated profile picture. Yes. Have it as your updated profile picture. Is case 1 and 2 okay? I give you the tasks. Yes. Is case 1 and 2 okay? I give you the tasks. Yeah, people want tasks. People want to leave this place. People are tired. People are tired. So the tasks. So I'll be happy when I see these equations in the what? In the discussion group. Now here, let me give you the name to confuse you. So phenyl ethanoic acid. Yes. You're supposed to do both alternatives. Of course, let me make people aware that we are writing the equations of ionization. Some of you may just write the structures and stop there. So let me hope another person has taken the screenshot of the tasks and you've posted them in the group. Now, I want you to breathe in and out. I want you to breathe in and out. We just have 5 minutes here. Bases are the easiest because bases have only one option. Bases have only one alternative. It's acids that are hard. Bases are not hard. They have one alternative. And you just need to understand what they are. Period. You just need to understand what they are. Nothing else. So for them, don't be worried. They are easy and you're also going to understand. So the good thing, you've understood acids. Now assume you've forgotten. Now I want you to believe that you're now learning something new. So the people who are on, don't leave. Whoever is listening to me, don't leave. Don't leave. The number that is there is very okay because we are going to learn something new and you've just changed slightly. Remember, we've been starting lessons at 10:30. Today we began at almost, I think we began at noon. So don't say that we have been here for so long. No, it's almost the same time. Because for today we started a bit late. So let's stay on for only and only 5 to 10 minutes. We do equations for bases, we go. And bases have one alternative. They are not like acids. Yeah. Let's do bases. Bases. So part C. Let's do the strong bases. Remember, the strong bases are 2. That means that is, I'm going to do only one, you do the other. So one thing I can say, because these ones are also strong, you shouldn't forget to use full arrows. So for me, I'll do the first one, which is sodium hydroxide. I even taught you this in alkyl halides. You know what it does? Full arrow. So it gives you, know where the boundary line is. So it will give you the sodium ions aqueous and the hydroxide ions aqueous. Like there is no alternative. Don't even waste your time. Don't even waste your time. It's just that. Yes, these ones have the hydroxide ions that we need. So we just get them. When you do other things, you'll be totally wasting time. So for bases, it's just like that. Just assume. Let me show you where the confusion comes in. Just assume this one is sodium ion, then this one is hydroxide ion. Then you come and add water. All we know that this water, okay, what do you even want the water to do? Because what we know that bases are proton acceptors. So if you want it maybe to accept a proton from water, remember water has the H plus and the O minus. It is very weird. It's like you will again form water. Okay, it doesn't even add up. Even if you try to do it, nothing can happen. Remember, we know bases as proton what? Acceptors. So it is only water available to provide that proton. Let's assume this is the proton. What's going to happen? This one interacts with this to get water again. So it's like you're doing nothing. And again, the other remaining thing is hydroxide ion, which was already here. So I think you see the confusion. So for strong ones, just write that equation that you know and leave it at that. Don't stress. Okay. So the task is potassium hydroxide. So you do it, just one equation, and post it in the discussion group. A serious student even does it now and posts it now. Now weak bases. You all know that weak bases, we begin with ammonia, then we got what? We got what? To all other amines, because this one is the father. We said that we begin with this one, then this one gives birth. The father of the amines, or the amines. And because this one is the chief weak base, even these ones come out to be what? Weak bases. Isn't it what we said? Now this is where the confusion is. And I want to see if really people know chemistry. Are you looking at the strong base we had, sodium hydroxide? It was just like that. Remember, they give us hydroxide ions in solution. The sodium hydroxide and the potassium hydroxide are organized in a way that the hydroxide ions we are supposed to produce are very clear. You just see them. Sodium hydroxide, and what do you expect? Hydroxide ions. It's just obvious. Even if someone doesn't know the structure, but when they hear that sodium hydroxide must give you hydroxide ions, they are like, the source is direct. But now look at a weak base like ammonia. We also expect hydroxide ions from it. But let's assume ammonia wants to copy what sodium does. Look here. Would be like, this is our ammonia, aqueous. But remember, for it is weak. So because they are weak, I don't want you to forget the fact that we are supposed to use partial ones. Okay, let me remove this arrow. You may think it's for the equations. But what I meant is that ammonia is the chief weak base. And is the father of all other amines. So because they are weak, the arrows are supposed to be what? Partial. Now, assuming ammonia wants to copy what sodium does. Hey, do you see any future? Remember, these are bases. They must give us hydroxide ions in solution. Do you see any future for ammonia? What can it really produce? Nothing. Nothing. I don't see anything ammonia can do. Because for sodium it was clear, and potassium, those ones were okay because they had OH within their structures. So you just need to put a boundary line, split them, and produce the hydroxide ions in solution. But now the ammonia, the chief of weak bases, how is it really going to have that equation? Because it's going to be a long story. It will be a long story. What do you think is the solution? Because it doesn't even have O in its structure. Remember we said ammonium hydroxide doesn't exist. What exists is the ammonia with aqueous, meaning ammonia solution, aqueous ammonia. So you people, I'm confused. If ammonia is to give us OH, how is it really going to do it? Because it doesn't even have O, but okay, it has the H. But where is O going to come from? Any ideas? Any ideas as I draw my structure here? Any ideas? People, when they say ammonia aqueous, this one means ammonia, then aqueous or solution, ammonia solution, aqueous ammonia means what? Water, isn't it? So water assists it. So when you say ammonia solution, solution means water. When you say aqueous ammonia, aqueous means what? Water. That means for these weak bases, water must be part. You don't have any alternative. You get? So with these ones, water must be part of the equation. Because we have realized there is no option. You remember other weak bases are amines. Amines don't have O anywhere. So that means it is the same story. Water must be part. Water must be part of the equations. Like there is no option. Yes, water must be part of the equations. So as you're writing these things, you're supposed to come and say, the ammonia, I want you to listen because other equations are yours. This is liquid. If you don't understand the chemistry and you just cram things, they will give you a time. Now look here. That's the equation. But now the concern is, what are we going to put the other side? What are we going to put the other side? You all know that this ammonia is a base, even besides it being weak. You all know bases accept protons. Isn't it? Accept protons. Now my question is, where are the protons going to come from? Where are the protons going to come from? Someone who can answer that, you either write in the chat or raise up your hand. I ask you to unmute and you speak. Where are protons? Where are protons? That is our equation. It's incomplete. The moment you answer that question, for you will have passed. You will enjoy chemistry for the rest of your life. So I want the answer. By saying from water, it will react with water. Okay, that is very good. I think people can see that. Ammonia is with water. It's with nothing else. It's with water. It's water that is there. So since the ammonia we are dealing with is a base, and for it to react, we expect it to accept protons. And it's only and only with water, like there are only two. We don't expect the proton from heaven. This is chemistry. So water must find ways of giving us that proton. So the answer is very easy, that water must provide. Water must, because it's the water that is available. It's the one that must provide. It's the one that must provide. Then you recall what I said. I told you that this water has two things. It has the H plus part and the OH part. You all know that. Now this one is our proton, this one. So because ammonia is a base, it will accept it. It will accept it, period. It will accept it. So when ammonia accepts the H+, someone may be like, what are we really going to form? Let me educate you a bit. You may either be this kind of student who is going to say, when ammonia accepts the H+, it becomes NH4. Not forgetting aqueous, isn't it? Because it has been NH3, but it is accepting H. So that H comes, it becomes NH4, but the H comes with a plus, and that plus sits on top of nitrogen. You get that? You get that? That it has been NH3 ammonia, and you expect it to accept a proton H+. So NH3 accepts H, it becomes NH4. But this H is coming with a plus which must sit on top of nitrogen. That is now what they call learning it in a friendly way. In a friendly way. Now, what if you want to know the real chemistry happening? This is it. You all know that ammonia is like this. I don't mind about the structure. I know it's trigonopyramidal. Anyway, let me draw what people want to see. You know, I also hate it when I do wrong chemistry. And you all know this bond in the middle shouldn't be straight. Then like that. You know that is the trigonopyramidal. And then you know nitrogen has a lone pair, isn't it? So this is the ammonia. So that lone pair can attract a plus. That's why ammonia is a base, because it can accept a proton. How does it accept it? A proton is H+. And these lone pairs of electrons on nitrogen, they are negative. So the attraction can happen. So that attraction is like the what? The acceptance, yeah? Get the point? So when this one happens, what do we have? We shall have our N. We shall have now the H, isn't it? We shall have our H. Then we shall have these other ones. But trust me, this nitrogen is getting a fourth bond, and nitrogen is stable with only and only 3 bonds, you know that. So that fourth bond makes it to have a what? A plus on top of nitrogen. Or they may just say enclose it at once and be like, this is it. You put the charge overall. But even when you put it, even when you do this, even when you put that plus on N, it's no problem. That's why you find so many people, if they don't do this structure, they will just do this and put it besides here. So this is the best. And you know why? The best. But then this one is what? Okay. So I don't want you to write this one and be like, maybe I failed, what. It is very okay. But even putting it on top of N, it's no problem. It's no problem. It's very clear and understandable that something bad has happened. Hope we are together there. So you either know this behind the scenes, or you just be like, it has been NH3, H plus has come in, it becomes NH4, but the H came with the plus. The plus make it sit on top of nitrogen. And then this OH minus is left. So it is left with no option other than being part of the products. Because for it cannot be accepted by the ammonia. So for it will have no option other than being part of the what? The products. And that is the correct equation. You get your 1.5 marks. So I don't know if people have realized how the hydroxide ions will be produced. So realize that water is playing the most important part in these equations. How? It is providing the proton the base must accept. It is providing the hydroxide ions that must be produced in solution by base. So when you're talking of strong bases, the sodium hydroxide and potassium hydroxide, just know you're supposed to just put a boundary line. split the sodium ion, hydroxide ion, the other side, you're done. But when you come to these weak ones, the way they look, they don't have O anywhere. So it's like they cannot even produce the hydroxide. So water must be part of the equations. And when water comes in, it splits into two. The proton, the base, must accept, and the hydroxide ions that must be what? Released. What have I said? The water splits into two. One, the proton, which must be accepted. Which must be accepted by base to form what you know. Then the OH, which must be released or produced in solution. Because you know, when we dissolve a base in water, we expect hydroxide ions to be part of the products. It is water giving us that hydroxide ion as the product. It is water providing the proton to be accepted by the base. That is all. Trust me, if you have that principle, you can do all the equations for all other bases. That is the one for ammonia, the father of all amines. It is done. Now let me show you the equation for methyl amine. Because now I believe you know the names. Yes, you know the names. This has been Roman 1. Let me show you Roman 2. You may think things are hard. They are not. So imagine the question is asking you for how methyl amine or methyl amine. In medical school, you call them amines. Yes, not amines. I don't know why, but that's how we used to call them when I was in my 4th year at Makerere University. That is, I think, 6 years back. So when this one is to ionize in water, we told you that water must be part. Just look at that one. It's methylamine and it's a base, isn't it? So we expect it to give us hydroxide ions in solution. But again, it doesn't have any O. So that's where the water comes in. Water, liquid. Because it is an amine and it's a father of, and it's a son or daughter to ammonia. And ammonia is the chief weak base. We know they are also weak bases. So the arrows we are using must be what? Partial. And then we know that it is water that is going to do it all. What do we mean? That this water will have the H plus part and this part. You get? And we all know that this proton is going to be accepted by this base. And then this hydroxide will be part of the products because we expect a base to give it to us in solution. So what happens when this base accepts this proton? We shall have our CH3, but you need to know who is accepting the H plus. It is the lone pair of electrons on N. Or if you just be like it is N, yeah, you be like, for me, I'm sure this proton is going to the N. Hey, so you come and be like CH3. So what has been NH2 becomes NH3. But I told you that incoming H comes with a plus, which plus must sit on N. And never forget the aqueous. Then the other OH must be part of the products. And it is aqueous like that. And that's how you get all your marks. I don't know if that is hard. Ethylamine. Ethylamine. I want you to look here. Ethylamine. It's an amine. People, we are done. Ethylamine. If you've understood for yourself, you know I should have the ethyl group. I taught you how they come about. Ethylamine, that means there is the ethyl group. And of course, the amino group like that. So this one is what? Is aqueous. It is a base. We expect it to give us hydroxide ions. Hydroxide ions have O, but they don't even have O. So water must come in because they are together in the beaker. They are not with anyone else except water. So the water is here and it is a liquid. Partial arrows. And what did we say? How does water do this thing? The water has two components. It has the proton component, which the base must accept, and then the OH component, which must be part of the products. What do we get when the H plus is accepted? We get CH3, CH2, then NH3. I don't know whether you're getting it. NH3. Because it has been NH2 here, so this H that is accepted makes it what? NH3, but the 3 came with a plus that sits on top of N. But if that plus is besides, don't think the answer is wrong. Maybe if it's like this NH3 and the plus is here, when you find it somewhere, don't be like, these people have wrong things. It's okay, but this is the best thing. What do you have? You have the aqueous. Then you shouldn't forget that the hydroxide ion will be part of the product this side. And that's how you get your complete marks. So you're supposed to understand the chemistry in each equation. When you understand the chemistry in each equation, things become easy. So I have a question. You people, you look at those three equations. The one of ammonia, the one of methylamine and ethylamine. Do you have any question, or you're ready for tasks? Just understand the chemistry within, that these are weak bases. Bases must accept protons. So you must ask yourself, where are they going to come from? These bases are in beakers where they are there with only water. So it's only water that should find a way and provide the protons we need. You understand? And in the due course of water providing water, by default, it even provides us with the hydroxide ions. And it's just a dream come true, because we are dealing with the base and we expect hydroxide ions on the product side. Let me tell you, as of now, the chemistry is seeming too much. But when you practice, you do like 5 and repeat the same thing over 5 times. You now come up with your own way of getting it. Appreciate the real chemistry, do the right thing, following the right principles. As you repeat it and repeat it and repeat it, time reaches and it's part of you. Time reaches and it's what? Part of you. So you people, any comment on that? Have it in mind. For acids, there are 2 alternatives, and we dealt with those. With bases, when we come to the strong ones, for them, they are clear. Even their names have the word hydroxide. So you just put a boundary line and split. But when we come to the weak ones, they don't even have O in their structures. That means water must come in. And water comes in, it provides 2 things. The proton we must accept, and the OH we must produce and be part of the products. How is this H plus accepted? If the N is NH2, it becomes NH3, and then the plus goes on top of N. So this H comes with its plus. On top of increasing the number of H's on nitrogen, it puts a plus on top of nitrogen. You know what causes that in real life or in real chemistry, and you know how you can just force it. Everything has been explained. Okay. Some of you are unfair. How can you say give us tasks we have not eaten lunch? You want to tell me who is over talking, who has talked for over 2 hours? You're more hungry and you have used more energy. You want to tell me that more energy is needed not to understand than to teach? Is it what you want to tell me? So the tasks, you people, I remember teaching you phenylamine. Which was like this. Let me see. Do people agree that it is the same as this? C6H5, then NH2. People, you tell me, is it the same thing or it's not? Is it the same as C6H6NH2? Is it the same? Are you sure it's the same? C6H6. Is it really C6H6? Is it really C6H6? What is it? What is it? Don't just say no. What is it? If it's not C6H6, then what is it? H5. That's what I wanted. It's H5. So you all know that it is before. It is H6. But we remove one hydrogen and we replace it with the amino group. I taught you that in benzene. And that's why you write it as H5. As simple as that. And you now know this one is preferred in equations and calculations. So you must consider that. So when they give you phenylamine, that is a better structure. And I also told you it's also called aniline. So this one is preferred in calculations. Preferred in calculations and equations. But of course we cannot prefer for you. So you can prefer the one with the benzene ring. Good thing I taught you. So you do that for me. You also do propylamine. I gave you the structure, so this time around let me use the names. You can do propylamine. Also do for me isopropylamine. Yes. Then you do for me this one. You can see that this one has no ring inside, so don't worry by putting a ring. I've not put anything like a ring. Now, this is it. This is it. For me, let me use this. This is mine. For me, let me use this. Then this one is yours. So as you're doing the task, consider this second structure. For me, let me use this one. It is very easy. So people know what we are doing. We are simply writing the equations of ionization. That's how questions usually come. Equations of ionization, or what I may call the equations of dissociation. And they usually use nomenclature. So you need to appreciate. So lastly, hey, you people, we have reached page 15. A lot of work has been covered. So lastly, look here. For me, let me use the benzene ring. So this is the aniline. And I told you put the aqueous somewhere here at the bottom of the ring. The water must be part, isn't it? Liquid. So we all know that this water provides two things. It provides the proton. This one is going to accept, and then the hydroxide, which will be part of the product. So when the proton is accepted, what happens? This one is NH3 and with a plus on top of N. Do you see that? Very nice structure. That is one of the structures I like in chemistry. It looks good. Yes, and it is called, it's called the phenyl ammonium ion. But we shall find it in hydrolysis. Right now we don't need to know its name, but it's called the phenyl ammonium ion. So you people, these things are not supposed to be part of your, they're not supposed to be part of your equation. It is just side work. By side work, the moment they see that is malpractice, you get your things wrong. So make sure your equations are neat with no side work. And I think that is the end. That is the end. People, first assure me that that equation is very okay. Do you make sense out of it? Do you see the water providing the proton? Do you see the NH2 becoming NH3 and the plus sitting on N? Because the proton not only comes with H but with also plus. Do you see the OH just being part of the products because that's what we expect of a base? Do you see the aqueous throughout and the water? Do you see that without water the equation can't happen? Trust me, if you don't read that work, it's going to look weird in a very little time. If you don't respect it, it will look very weird. And failure to have the right equation, you cannot have the right expressions of K and KB, you cannot calculate. If you can't calculate, you don't even understand salt hydrolysis, you don't understand buffer solutions. Maybe God may help you and you understand salt beta equilibria, but this is the basis of whatever we are going to cover. So this is the real foundation of ionic equilibria. Otherwise, if I go back to my very first page, I can see that now the equations of ionization in each case, all the 4 cases I've handled. Assignment and research, I've given you more assignments and more research. So our next stop are calculations. Our next stop, calculations. Do you need this workbook? Should I share it after? So you people, I'm done. Eh? Maybe if you just want to listen to the next stop, then you go. So next stop is derivations of Ka, and Kb dissociation constants. Sure, let me just say expressions and stop there. So you make research. You can make research. Yes, ask yourself, what is Ka? What is Kb? But I'll be happy that as people are having lunch, you take a bite, you write one equation. Take a bite, write one equation. Take a bite, write one equation. As you make research about K and Kb. Otherwise, allow me sign out. Allow me sign out as Paul Tutor. A science math tutor at Science Scholars Academy Uganda, and my contact is 0753279592. Yeah, and I really prefer WhatsApp calls. So those wanted to Gand it, please you Gand it. Prefer WhatsApp calls for immediate response. Otherwise, thank you for attending. Also, people, when I don't tell people to appreciate me for the lesson, they don't, they just leave. Okay. Let me end the meeting as you're still thanking me. Those things of indiscipline are not good. Okay, people, we meet at night, same topic, and see how we can progress. Otherwise, thank you for attending, and bye-bye.